A quantum computer is not simply a faster version of the machine on a desk. It works by controlling qubits' phase entanglement and interference so precisely that certain problems can be approached in ways classical computers cannot easily reproduce. That difference is what makes quantum computing both promising and difficult. The same fragile quantum states that create new possibilities are also constantly threatened by noise decoherence and error. Like a subscription or a share helps support more calm, carefully researched science journeys like this one. And wherever this video has reached, you feel free to leave a comment with your city or country, what time it is there, and whether you are listening while studying, relaxing, or getting ready for sleep. Thank you for spending part of your time watching. From the first qubit to quantum gates, famous algorithms, error correction, and the machine still being built, the story can now unfold slowly from the foundations upward. Quantum computing begins with a distinction that sounds simple, but changes almost everything that follows. A classical computer stores and transforms information using bits, while a quantum computer stores and transforms information using quantum systems called qubits. That difference is not merely a change in hardware. It changes the mathematical language used to describe information, the kinds of transformations that can be applied to it, and the strategies available for solving certain problems. A classical bit is represented as one of two states usually called 0 and 1. A qubit also has two basic reference states, but quantum mechanics allows its state to be described by amplitudes associated with both of them. Those amplitudes can interfere with one another, and several qubits can become entangled so that the state of the whole system cannot be reduced to a collection of independent parts. These features are the reason quantum computation is treated as a different computational model rather than simply a faster version of the familiar one. The word faster can be misleading because most ordinary tasks do not become automatically easier on a quantum processor. Writing a document, displaying an image, sorting a modest list, running an operating system, or handling routine web traffic does not acquire some universal acceleration merely because qubits are available. Classical computers are extremely effective at these jobs, and they remain the natural machines for an enormous range of calculations. Quantum computers become interesting where the structure of a problem can be matched to quantum behavior in a useful way. In those cases, an algorithm may arrange amplitudes, phases, and correlations so that certain computational paths reinforce one another while others are suppressed. The final measurement still produces ordinary classical information, but the route taken before that measurement can be fundamentally different from a classical calculation. This is why the central promise of quantum computing is selective rather than universal. The goal is not to replace every transistor with a qubit. It is to discover where quantum mechanical structure provides an advantage that is large enough to matter. Some of the clearest examples come from problems whose mathematics already has a strong relationship with quantum systems. Simulating molecules and materials is a natural case because chemistry itself is governed by quantum mechanics. A classical computer can model quantum systems, but the resources required can grow extremely quickly as the number of interacting particles increases. A quantum computer, at least in principle, can represent certain aspects of such systems more directly because its own state follows quantum rules. That does not make quantum simulation easy and practical. Usefulness still depends on hardware quality, error rates, algorithm design, and scale, but it explains why simulation has remained one of the field's most persistent motivations. Another famous example comes from number theory. Shor's algorithm showed that a sufficiently capable quantum computer could factor large integers and solve related discrete logarithm problems much more efficiently than the best-known classical approaches of the same kind. The importance of this result does not come from factoring being a common everyday task. It comes from the fact that several widely used public key cryptographic systems rely on mathematical problems believed to be difficult for classical computers at large enough sizes. Quantum computing therefore matters not because it speeds up everything, but because a speed up on one carefully chosen problem can have consequences far beyond that problem itself. Grover's algorithm illustrates a different kind of advantage. It does not turn an unstructured search into an effortless task. But in an idealized oracle model, it reduces the number of required queries from a quantity that grows linearly with the search space to one that grows roughly with its square root. That improvement is significant, yet it is also limited. It shows that quantum speedups come in different forms with different assumptions and different practical value. Some are dramatic in theory, some are more modest. Some may disappear once the cost of loading data, correcting errors, or implementing the required circuit is included. This is one reason careful discussions of quantum computing distinguish between mathematical speedup, experimental advantage, and real-world usefulness. They are not the same claim. A quantum algorithm can be asymptotically better on paper without being practical on available hardware. A laboratory experiment can perform a specialized task beyond convenient classical simulation without creating immediate commercial value. A useful quantum application would require not only a theoretical advantage but also a machine capable of running the necessary computation accurately, repeatedly, and at a total cost that makes sense compared with classical alternatives. The difference between quantum and classical computing also appears in the way information is manipulated. Classical logic can copy bits freely, inspect intermediate values, and use irreversible operations without violating the basic rules of classical physics. Quantum information is more constrained. An unknown quantum state cannot be copied perfectly by a general operation. An ideal quantum evolution is described by reversible transformations. Measurement must also be treated carefully, because it does not merely reveal every detail of a quantum state without consequence. A measurement produces an outcome according to probabilities determined by the state, and that process changes what can be said about the system afterward. These constraints are not inconveniences added to an otherwise ordinary computer. They are part of the computational model itself. Quantum algorithms are designed around them. The same physical rules that make qubits powerful also make them difficult to control. A useful quantum processor must prepare delicate states, preserve phase relationships, create controlled interactions between qubits, and perform measurements with very low error. It must do this while the environment constantly threatens to disturb the information being stored. Heat, electromagnetic noise, imperfect control pulses, material defects, unwanted coupling, and measurement inaccuracies can all degrade a computation. This is why a machine with more qubits is not automatically a better machine. A small processor with highly reliable operations can be more informative for some experiments than a larger processor whose errors accumulate too quickly. The real challenge is to scale both quantity and quality at the same time. That challenge leads directly to one of the deepest ideas in the field: quantum error correction. Instead of trusting a single fragile physical qubit, error correction spreads logical information across many physical qubits and repeatedly checks for patterns that reveal whether errors have occurred. The protected information is not simply copied in the classical sense. It is encoded into a larger quantum state so that certain disturbances can be detected and corrected without directly reading the information itself. The cost can be substantial, which is why estimates for large fault-tolerant quantum computers often involve far more physical qubits than the number of logical qubits actually used by an algorithm. The size of that overhead depends on hardware quality code, design, target error rates, and the computation being attempted. This gap between a physical qubit and a useful logical qubit is one of the most important distinctions in understanding where the field stands. Present quantum processors can already be programmed, controlled, and used for sophisticated experiments. They are not hypothetical machines. Yet they also remain limited by noise, finite coherence, imperfect gates, and restricted circuit depth. The most meaningful question is therefore not whether quantum computers exist. They do. The harder question is what level of computation they can perform reliably, and whether that level can be expanded until useful algorithms exceed what classical machines can achieve at acceptable cost. That question keeps the field suspended between established physics and unfinished engineering. The theoretical foundation is strong enough to show that quantum computation is genuinely different. The experimental foundation is mature enough to manipulate real qubits in many physical platforms. The engineering foundation is advancing, but it has not yet closed the distance between impressive laboratory systems and broadly useful fault-tolerant machines. Seen in that light, quantum computing becomes easier to place. It is neither a magical replacement for classical computation, nor an empty promise built on exotic terminology. It is a specialized approach to computation based on the controllable evolution of quantum states, with known advantages for some problems, possible advantages for others, and major technical barriers still standing between present devices and their most ambitious applications. The next step is to look at the object carrying all of this potential, because almost every later idea in quantum computing depends on understanding what a qubit actually is and what it is not. A qubit is easiest to misunderstand when it is described as a strange version of a classical bit. The comparison is useful only at the beginning. A classical bit occupies one of two definite states usually called 0, and one and every larger classical data structure is built by arranging many such bits into patterns. A qubit also has two reference states that are usually labeled 0 and 1. But those labels do not mean that the qubit behaves like a tiny switch that secretly chooses one value while hiding the other. Its state is described by a quantum state vector, and that state can include an amplitude associated with the 0 basis state and another amplitude associated with the 1 basis state. These amplitudes are not ordinary probabilities. They are mathematical quantities whose magnitudes help determine measurement probabilities, while their relative phase affects how the state changes when quantum operations are applied. That distinction is central. If a qubit were only a classical random bit with a hidden chance of being 0 and a hidden chance of being 1, much of quantum computing would disappear. A classical probability distribution can describe uncertainty about which definite state a system occupies. A qubit instead can occupy a coherent quantum state in which the amplitudes themselves can be transformed and made to interfere. The difference is subtle in language because both descriptions can lead to probabilistic measurement outcomes, but they are not the same physical situation. Suppose a qubit is prepared in a state that gives equal measurement probabilities for 0 and 1 in the standard basis. A classical coin toss can also produce equal probabilities, yet the qubit may still carry phase information that the coin does not possess. By applying a suitable quantum gate before measurement, that phase information can be converted into a change in observable probabilities. Two quantum states can therefore produce identical statistics in one measurement basis while behaving differently under later operations. This is one reason the phrase half 0 and half 1 is inadequate. It describes neither the full mathematical state nor the physical possibilities available to the computation. The usual language of a qubit begins with a two-dimensional complex vector space. The two basis states provide reference directions, and the state of the qubit is written as a combination of those basis states with complex amplitudes. Complex numbers matter because quantum mechanics requires both magnitude and phase. The magnitude of an amplitude contributes to the probability of a measurement outcome, while the phase becomes important when amplitudes are later combined. A global phase shared by the entire state has no observable effect, but relative phase between components can change interference. This means that two states with the same measurement probabilities in the computational basis can still represent different qubit states because their relative phases differ. In a classical setting, probabilities alone can often summarize uncertainty. In a quantum setting, probabilities are not enough. The amplitudes contain more structure than the final measurement statistics reveal. When a qubit is measured in the computational basis, the probability of obtaining 0 is given by the squared magnitude of the amplitude associated with the 0 state, and the probability of obtaining 1 is given by the squared magnitude of the amplitude associated with the 1 state. These probabilities must add to 1, so the amplitudes are constrained by a normalization condition. Measurement does not expose the amplitudes directly. A single measurement returns one classical result, either 0 or 1. Repeating the same preparation and measurement many times allows the probabilities to be estimated, but even that does not automatically reveal the complete state, because phase information may remain hidden. Recovering a full description requires measurements in different bases and enough repeated trials of procedure related to quantum state tomography. This gap between the richness of the state and the narrowness of a single measurement is one of the defining features of quantum information. A qubit can store a continuously variable quantum state, but that does not mean one qubit can be read out as an arbitrarily large amount of classical information. The measurement process sharply limits what can be extracted in one run. Quantum computing gains its power not by treating amplitudes as a secret memory bank that can be opened at the end, but by transforming those amplitudes during the computation so that useful global properties influence the probabilities of a small number of measured outcomes. The block sphere provides a geometric way to picture a single qubit without pretending that the geometry is the physical object itself. After ignoring the physically irrelevant global phase, every pure state of one qubit can be represented by a point on the surface of a sphere. The north and south poles correspond to the two computational basis states, while points around the equator correspond to balanced superpositions whose relative phases differ. Moving around the sphere represents changing the state through quantum operations. A rotation around one axis changes the state differently from a rotation around another, and familiar single qubit gates can be understood as particular rotations or combinations of rotations. The block sphere is valuable because it makes one fact visually clear. There are infinitely many pure qubit states between the two basis poles, yet the sphere must also be used carefully. It applies neatly to one isolated qubit in a pure state, while larger entangled systems cannot be represented by simply giving each qubit its own independent Bloch sphere. Once qubits become entangled, the most important information can live in correlations across the joint system, rather than in the state of any single qubit viewed alone. Physical qubits can be built in many ways because 0 and 1 are not tied to one specific material object. They are labels for two quantum levels chosen to encode information. In a superconducting circuit, the logical basis may be associated with two energy states of an engineered electrical system. In a trapped ion, it may be encoded in two internal atomic states. In a neutral atom, a spin system, or a photonic platform, different physical degrees of freedom can serve the same abstract computational role. The hardware changes, but the mathematical requirements remain closely related. The system must provide two distinguishable quantum states, allow controlled transformations between coherent combinations of them, preserve the state long enough to perform operations, interact with other qubits when needed, and support reliable measurement. This is why the word qubit describes both an abstract unit of quantum information and a physical implementation problem. The abstraction is simple enough to write on paper. The physical realization is when noise-unwanted coupling thermal effects, material imperfections and control limitations enter. Even at the level of one qubit, there is already a tension between mathematical elegance and experimental fragility. An ideal qubit evolves exactly according to the intended quantum operation. A real qubit is never perfectly isolated. Its amplitudes and phase relationships can drift or become correlated with the environment, gradually destroying the controlled quantum state. This loss of coherence is not merely an inconvenience for later engineering. It shows that a qubit is valuable precisely because it retains information in a form that classical bits do not. The same phase structure that enables interference is also vulnerable to disturbance. The same coherent control that allows a state to move smoothly across the block sphere must be achieved without allowing uncontrolled interactions to scramble that motion. Understanding the qubit therefore means holding several ideas together at once. It has two reference states, but infinitely many pure states. It produces classical outcomes when measured, but cannot be reduced to a classical random variable before measurement. Its amplitudes determine probabilities, yet phase can matter, even when those probabilities initially look identical. It can be represented geometrically for a single isolated system, but that picture becomes incomplete when multiple qubits share an entangled state. Most importantly, a qubit is not powerful because it somehow contains every answer at once. Its value comes from the fact that amplitudes can be prepared, rotated, correlated, and later made to interfere under carefully designed operations. The next step in that picture is superposition, not as a slogan about being in two places at once, but as the precise structure that allows a qubit state to contain coherent contributions from more than one basis state and still preserve the phase relationships on which quantum computation depends. Superposition is often introduced as the point where quantum computing begins to sound impossible, because a qubit is said to be 0 and 1 at the same time. The phrase is memorable, but it hides more than it explains. A superposition is not a contradiction in which a system holds two ordinary classical values simultaneously. It is a quantum state described as a coherent combination of basis states, with an amplitude attached to each component. For a single qubit, those basis states are usually labeled 0 and 1. The amplitudes tell the mathematics how strongly each component contributes to the total state, while their relative phase determines how those contributions can later interfere. This is why superposition must be understood together with amplitudes and phase, rather than as a vague statement about multiple realities. A qubit can be prepared in the 0 state, and then transformed by a quantum gate, so that its state becomes an equal superposition of 0 and 1. The Hadamard gate is a standard example. Applied to the 0 state, it produces a state whose two basis components have equal magnitude. If that qubit is immediately measured in the computational basis, the outcomes 0 and 1 appear with equal probability over many repeated runs. Yet that statistical result alone does not reveal the full state. Another equal superposition can produce exactly the same measurement probabilities while carrying a different relative phase. Those two states may look identical if measured immediately in one basis, but they respond differently to later gates. The distinction becomes visible through interference. This is the first important correction to the usual explanation of superposition. The amplitudes are not merely hidden probabilities waiting to be sampled. They are quantities that can combine according to quantum rules and phase controls, whether their contributions reinforce or oppose one another. Probability enters only when measurement is made. Before measurement, the algorithm manipulates amplitudes. The probability of observing a particular basis state is obtained from the squared magnitude of its amplitude, but the amplitude itself may be positive, negative, or more generally complex, and those differences matter during the computation. Two pathways can contribute amplitudes toward the same final outcome. If the phases align, the amplitudes can add and make that outcome more likely. If they oppose, they can cancel and make the outcome less likely, or even remove it entirely. This ability to reshape probabilities by controlling phase is one of the central tools of quantum algorithms. Without it, a superposition would be much less useful. Creating many possible components is only the beginning. A computation has to arrange them so that the final measurement is biased toward information that matters. The same idea scales when several qubits are combined. Two classical bits can occupy one of four configurations at a time. 0001110 or 11. Two qubits have a joint quantum state that can contain amplitudes for all four basis configurations. 3 qubits have amplitudes for 8. Each additional qubit doubles the number of basis states needed to describe a general pure state of the whole register. With many qubits, the mathematical state space becomes enormous very quickly. This exponential growth is one reason quantum computers attract so much attention. A general state of a large quantum register cannot usually be written down or tracked efficiently on an ordinary classical computer using a simple list of all amplitudes because the number of entries doubles with each qubit. Yet this does not mean that a quantum computer automatically performs an exponential number of ordinary calculations and then reveals all the answers. Measurement does not provide a printout of every amplitude. A measurement of the register produces one classical bit string per run. Repeating the circuit can reveal statistical patterns, but it still does not expose the entire state directly. The real challenge of quantum algorithm design is therefore to use the huge state space indirectly. The algorithm prepares a structured superposition, applies transformations that encode some feature of the problem into phases and correlations, then uses interference to concentrate observable probability into outcomes that reveal that feature. The state space is a computational resource only when it can be controlled in this disciplined way. A random superposition over an enormous number of basis states is not automatically useful. In fact, if all outcomes remain equally likely at the end measurement may reveal very little. The power lies not in the number of components alone, but in the pattern of amplitudes across them. This is why the phrase quantum parallelism has to be handled carefully. It can be helpful as an intuition for the fact that a quantum operation acts linearly on all components of a superposition. If a register contains amplitudes over many basis states, a suitable quantum gate transforms the whole state at once, according to the same underlying operation. But the phrase becomes misleading if it suggests that each component is an independent classical computer, whose result can later be read separately. The components are parts of one quantum state. They can interfere, become entangled, and contribute jointly to the final measurement statistics. What can be extracted is constrained by quantum measurement. An algorithm must therefore arrange the computation so that the desired global property becomes easier to observe than the individual hidden details. This is exactly what makes quantum algorithms unusual. They often seek a property of a function, a period, a phase, a parity, or some other global structure rather than attempting to recover every intermediate value. Superposition also depends on coherence. The amplitudes must preserve definite phase relationships long enough for later interference to work. If uncontrolled interactions with the environment disturb those relationships, the state can begin to behave more like an incoherent statistical mixture. A mixture may produce the same immediate probabilities as a coherent superposition in one measurement basis, yet it lacks the phase structure needed for the same interference effects. This difference is experimentally crucial. A qubit that merely gives half 0 and half 1 is not enough. The device must preserve the coherent relationship between the two components so that later gates can reverse rotate or recombine them predictably. One simple sequence shows this clearly. A qubit begins in 0. A Hadamard gate creates an equal superposition. If the qubit is measured immediately, 0 and 1 appear with equal frequency. But if no measurement is made and a second Hadamard is applied under ideal conditions, the state returns to 0. The first gate did not simply randomize the bit. If it had created an ordinary 50-50 classical mixture, the second gate could not deterministically reconstruct the original zero state. The recovery occurs because the amplitudes retain phase information and interfere in a precisely organized way. One pathway reinforces the zero outcome while another cancels the one outcome. The example is simple, but it contains much of the logic that later quantum algorithms expand into far larger circuits. Superposition creates alternatives within the mathematical state. Gates alter their amplitudes and phases. Interference reshapes which alternatives remain likely when measurement finally occurs. With several qubits, these components can also become entangled, making the joint state impossible to describe as separate independent superpositions for each qubit. That is where the size of the state space becomes connected to a second distinctly quantum resource. Yet even before entanglement enters, superposition has already changed the meaning of information processing. A classical register follows one definite configuration through each step of a deterministic computation or one sampled trajectory if randomness is introduced. A quantum register evolves as a state vector containing coherent components whose relationships matter as much as their individual magnitudes. This does not allow every conceivable answer to be extracted at once. It provides a different medium in which computation can be arranged. The useful question is never simply how many possibilities have been placed into superposition. The useful question is whether the algorithm can control the relative amplitudes well enough to make a hidden structure observable at the end. That distinction separates a genuine quantum computation from the popular image of a machine casually testing every answer in parallel. Superposition enlarges the space in which the computation can move, but it does not choose the direction. The direction comes from carefully designed transformations, and once several qubits are involved, one of the most important of those transformations is the creation of entanglement, where information stops belonging cleanly to individual qubits and begins to reside in the state of the whole system. Entanglement begins where the description of individual qubits stops being enough. Two qubits can each be prepared independently, manipulated independently, and measured independently. But quantum mechanics also allows them to occupy a joint state whose structure belongs to the pair as a whole. In such a state, it may no longer be possible to assign a complete pure state to the first qubit and another complete pure state to the second, and then combine those descriptions to recover the total system. The information is instead encoded in correlations between them. This is the defining feature of entanglement, and it makes multi-qubit quantum systems fundamentally different from collections of isolated quantum objects. A simple example begins with two qubits initialized in the zero state. A Hadamard gate can place the first qubit into an equal superposition of 0 and 1. A controlled operation can then link the second qubit to the first, producing a state in which the pair has amplitude for 0, 0 and 1, 1, while the other two computational basis states have no amplitude at all. Neither qubit considered by itself has a definite pure state corresponding to 0 or 1. If either one is measured in the computational basis, each result appears with equal probability, yet their outcomes are perfectly correlated. Whenever the first is found in 0, the second is also found in 0. Whenever the first is found in 1, the second is also found in 1. The important point is not merely that the measurements match. Classical systems can also be correlated. Two cards can be prepared so that both carry the same hidden value, and observing one can reveal information about the other. Entanglement goes further because the quantum correlations cannot always be reproduced by assuming that each object carried a complete set of predetermined local properties waiting to be uncovered. When measurements are performed in different carefully chosen bases, entangled systems can produce statistical patterns that violate Bell inequalities, mathematical limits obeyed by broad classes of local hidden variable models. Experiments have repeatedly observed these quantum correlations, making entanglement not a philosophical decoration around quantum mechanics, but a measurable feature of nature. Still, the word correlation can create another misunderstanding if it suggests that one qubit sends an instantaneous message to the other when measured. Entanglement does not provide a method for faster-than-light communication. The outcome observed on either side of an entangled pair is locally random. One experimenter cannot choose whether a measurement returns 0 or 1, and therefore cannot encode a controllable message into that outcome. Only after results from the two locations are compared through ordinary classical communication does the correlation become visible. The joint statistics can be stronger than classical intuitions allow, but they cannot be used to transmit usable information outside the causal limits imposed by relativity. This distinction is essential because entanglement is strange without being a loophole in the speed of light. Its power lies in the structure of a joint quantum state, not in hidden superluminal signaling. In quantum computing, this joint structure becomes a resource because algorithms often need information to be distributed across relationships among qubits rather than stored in each one separately. A register of independent qubits can already occupy a superposition over many basis states, but an entangled register can represent patterns that cannot be decomposed into separate choices for each qubit. As the number of qubits grows, those correlations can become increasingly complex. The state of the full system may contain dependencies that only make sense when many qubits are considered together. This does not mean that entanglement by itself guarantees computational advantage. A poorly designed circuit can create large amounts of entanglement without solving anything useful, and some quantum processes with limited forms of entanglement can still be simulated efficiently on classical machines. What matters is how the entanglement participates in the broader algorithm, how it helps encode a problem, distribute phase, information, constrain possible outcomes, or support interference that would otherwise be difficult to reproduce. The creation of entanglement is usually described through multi-qubit gates. A controlled NOT gate is one of the simplest examples. It acts on two qubits, treating one as a control and the other as a target. In the computational basis, the target is flipped when the control is in the 1 state and left unchanged when the control is in the 0 state. If the control is already in a definite basis state, this can look almost classical. If the control is in a superposition, however, the same operation can correlate the branches of the joint quantum state. One component may leave the target unchanged while another flips it, and the resulting state can become inseparable. The gate does not measure which component was present. It transforms the amplitudes, coherently preserving the phase relationships that later operations may use. This shows why entanglement belongs naturally beside superposition, rather than after it as an unrelated effect. Superposition creates multiple coherent components. Controlled interactions can connect those components across different qubits, producing correlations that exist at the level of the whole register. Once entanglement is present, the state of one qubit may appear locally mixed, even though the complete multi-qubit state is perfectly pure. This apparent loss of information is not necessarily caused by noise. It can arise simply because part of an entangled system is being considered while the rest is ignored. The missing information resides in correlations. That feature becomes important later in quantum error correction, where logical information is deliberately spread across several physical qubits, so that no single qubit carries the protected state on its own. It also appears in quantum teleportation, where entanglement and classical communication together allow an unknown quantum state to be transferred from one location to another without sending the original physical system itself. Even there, the process does not violate relativity, because classical information must still travel between the locations before the transferred state can be reconstructed. Entanglement also affects how quantum computers are built. A useful processor does not need only high-quality individual qubits, it needs controlled interactions between them. The pattern of which qubits can directly interact is called connectivity, and different hardware platforms provide different connectivity structures. Some devices allow strong local coupling between nearby qubits. Others can create interactions across greater physical distance by using shared modes, mobile atoms, photons, or more elaborate control techniques. Limited connectivity can force an algorithm to insert additional operations merely to move quantum information into positions where the required entangling gates can occur. Those extra gates increase circuit depth and create more opportunities for error. Entanglement is therefore both a theoretical resource and an engineering demand. It must be generated where needed with high fidelity without introducing enough noise to erase the very correlations being created. The fragility of entanglement also reveals something deeper about decoherence. When a qubit interacts uncontrollably with its surroundings, it can become entangled with environmental degrees of freedom. Information that was previously available within the controlled register then spreads into correlations with objects that are not being tracked. From the perspective of the quantum computer, coherence is lost. The environment has effectively acquired information about the system, even if no human observer performs deliberate measurement. This connection between entanglement and decoherence means that the same mathematical structure can be either useful or destructive, depending on what becomes correlated with what. Entanglement deliberately created among computational qubits can support an algorithm. Uncontrolled entanglement with the environment can destroy it. This dual role is one reason quantum hardware must balance isolation with interaction so carefully. Qubits must be protected from unwanted coupling, while remaining controllable enough to interact strongly on command. Too much isolation makes computation difficult. Too much uncontrolled interaction makes coherence disappear. Entanglement therefore sits at a threshold between the abstract and the practical sides of quantum computing. It demonstrates that quantum information can reside in relationships that have no classical counterpart, yet those relationships must be engineered with extraordinary precision if they are to become computationally useful. It does not allow instantaneous communication, does not guarantee speed up on its own, and does not mean that distant particles exchange secret signals. What it provides is a way for the state of a multi-qubit system to become more than the sum of independent qubit descriptions. Once that happens, the computation can manipulate correlations distributed across the whole register. But those correlations alone still do not decide which outcomes become likely. For that, the amplitudes of the joint state must be made to reinforce and cancel in carefully controlled patterns. And that movement from correlation into selective amplification leads directly to quantum interference. Quantum interference is the point where superposition begins to become computational rather than merely descriptive. A quantum state can contain amplitudes for many basis states, and entanglement can connect those amplitudes across several qubits, but neither feature guarantees that a useful answer will emerge when the system is measured. If all possibilities remain equally weighted, measurement may return a result that is no more informative than a random sample. The decisive step is to shape the amplitudes before measurement. Quantum algorithms do this by controlling phase so that some contributions combine constructively, while others combine destructively. Constructive interference occurs when amplitudes aligned in phase reinforce one another. Destructive interference occurs when amplitudes with opposing phase partially or completely cancel. The language resembles interference in water or light, but the object interfering is not a visible ripple moving through space. It is the mathematical amplitude associated with possible measurement outcomes. The consequences become observable only through the probabilities that appear after those amplitudes have been transformed. A simple single-qubit circuit already contains the essential idea. A qubit begins in the zero state. a Hadamard gate creates an equal superposition of 0 and 1. At that point, an immediate measurement would return either result with equal probability. If another Hadamard gate is applied without disturbing the qubit, the amplitudes are recombined. The contributions leading to 0 add, while those leading to 1 cancel, returning the state to 0, with certainty in the ideal case. Nothing has been tested in the ordinary sense, and no hidden list of 2 answers has been opened. The circuit has changed the relative phase, and then allowed different computational pathways to meet again. The result is determined by how their amplitudes combine. This small example matters because larger algorithms often use the same logic on a far more elaborate scale. They create a structured superposition, transform parts of that state so that relevant information appears in relative phases, and then apply further operations that convert those phases into measurable differences in probability. Phase is therefore not an ornamental detail attached to a qubit. It is one of the principal carriers of computational structure. 2 states can have identical measurement probabilities in the computational basis and still behave differently because the signs or complex phases of their amplitudes differ. A later gate can bring those components together and expose that hidden distinction through interference. This is why measuring too early can destroy the computation. Measurement replaces the coherent state with a classical outcome and removes the network of phase relationships that later gates were meant to exploit. A quantum algorithm must preserve those relationships until the interference pattern has done its work. The often repeated claim that a quantum computer tries every answer at once misses this mechanism. A register may indeed contain amplitudes over a very large number of basis states, but if each branch simply carried a candidate answer and nothing more happened, there would be no way to read all of those candidates at the end. One measurement still produces only one classical outcome. The algorithm needs a way to make information about many components affect that single final distribution. Interference provides that route. Instead of asking the machine to reveal every path, the circuit arranges for paths associated with unwanted structure to cancel, and for paths associated with useful structure to reinforce. The algorithm extracts a pattern from the whole state, rather than a transcript of each component. That distinction is especially clear in amplitude amplification, the idea underlying Grover's search algorithm. In an unstructured search problem, the desired item is initially only one possibility among many. A quantum procedure can prepare a superposition over candidate states mark the desired state by changing its phase, and then apply another transformation that redistributes amplitudes across the register. Repeating this carefully chosen sequence gradually increases the amplitude of the marked state, while decreasing the amplitudes of the others. The process does not instantly identify the answer, and it does not eliminate the need for measurement. Instead, it rotates the state through a mathematical space so that measurement becomes increasingly likely to return the desired candidate. Too many repetitions can even move the probability away from the target again, showing that interference must be timed rather than simply applied without limit. The gain comes from controlled evolution, not from an unlimited parallel search. Other quantum algorithms use interference in different ways. In period finding procedures related to Shor's algorithm, the aim is not primarily to amplify one marked item. The circuit creates a state containing information about a repeating mathematical structure, and then applies a quantum Fourier transform which reorganizes amplitudes according to their phase relationships. Certain frequencies reinforce while others are suppressed, making the hidden periodicity visible in the measurement statistics. The measured values do not directly state the factors of the original integer. Classical processing is still required to interpret them. Yet the crucial quantum step is possible, because phase information distributed across many components is made to interfere in a way that exposes global structure. Quantum phase estimation follows a related principle. It encodes information about an eigenvalue into relative phases and then converts that phase information into a form that can be measured. The details differ from one algorithm to another, but the recurring pattern is consistent. Useful quantum computation depends on arranging amplitudes so that the final probability distribution contains more accessible information than the initial one. This also explains why random quantum circuits, despite being difficult to simulate in some regimes, are not automatically useful algorithms. Complexity alone is not enough. A state can become extraordinarily complicated without concentrating probability on anything that answers a meaningful question. The circuit needs a designed relationship between the problem, the phase changes it introduces, and the interference pattern produced before measurement. Algorithm design therefore resembles a form of choreography. Gates do not merely move information from place to place. They control how different components of the state accumulate phase, how those components are mixed together again, and which outcomes survive the resulting cancellations. The mathematics is linear and exact in the ideal model, but useful interference can be extremely sensitive to error. If a gate applies the wrong rotation, if two qubits acquire an unintended phase shift, or if the environment partially reveals which computational pathway the system followed, the interference pattern can weaken. The amplitudes may no longer cancel where they should or reinforce where intended. This is one reason coherence is so important. Interference depends on preserving relationships between components, and decoherence damages those relationships by allowing information to leak into uncontrolled surroundings. In classical computation, a small physical disturbance may flip a bit and create a local error. In quantum computation, even a disturbance that does not immediately change a measured bit value can alter phase and corrupt later interference. The error may remain hidden until several gates afterward when a cancellation fails to occur. This sensitivity helps explain why gate fidelity and error correction become central as quantum circuits grow deeper. Interference also gives quantum computation an unusual relationship with reversibility. Ideal quantum gates are unitary, meaning that they preserve the total probability encoded in the state while redistributing amplitudes and phases. An operation can move probability away from one set of outcomes only by moving it somewhere else. Destructive interference at one outcome does not cause probability to vanish from the universe. The amplitudes are transformed so that probability appears in other outcomes when the entire state is considered. This conservation places strict constraints on algorithm design. A quantum circuit cannot simply erase all wrong answers and leave the right one behind by decree. It must construct a reversible sequence in which amplitude flows through the state space and interference changes where measurement probability accumulates. That is why many algorithms contain steps that seem indirect from a classical perspective. They may compute auxiliary information and code a phase, and then uncompute temporary data, so that unwanted correlations disappear while the useful phase effect remains. The goal is often to leave behind not a conventional record of every intermediate calculation, but a carefully sculpted pattern of amplitudes. Seen this way, interference is less a mysterious extra feature than the organizing principle that makes superposition useful. Superposition provides components. Entanglement can distribute relationships across qubits. Gates control how those components evolve. Interference decides how their amplitudes combine when different computational pathways are brought together. Measurement then samples the distribution that this entire process has produced. The power of a quantum algorithm comes from designing these stages so that a property difficult to extract classically becomes statistically accessible after the interference has reshaped the state. This is also why there is no universal recipe that turns every problem into a quantum speedup. The problem must possess enough exploitable structure for an algorithm to encode meaningful phase relationships and then convert them into useful interference. Where that structure exists, the effect can be profound. Where it does not, quantum mechanics offers no automatic shortcut. Interference therefore narrows the promise of quantum computing at the same time that it explains it. The machine is not powerful because it contains many possibilities. It is powerful when those possibilities can be made to cancel and reinforce with enough precision that the final measurement reveals something the initial state concealed. The next question is how such precision is imposed physically and mathematically, because every deliberate phase shift rotation, conditional interaction and recombination in a quantum computer is carried out through the operations known as quantum gates. A quantum gate is the controlled operation that turns an abstract qubit state into a computation. The comparison with a classical logic gate is useful at first because both are elementary transformations arranged into larger circuits, but the similarity ends quickly. A classical logic gate typically takes definite bit values as input and produces definite bit values as output. A quantum gate acts on amplitudes and phases, transforming the entire quantum state according to the rules of quantum mechanics. If a qubit is in a superposition, the gate does not first decide which basis state is really present. It acts coherently on the full state. If several qubits are entangled, a gate applied to part of the register can change the structure of the joint state as well. This is how quantum circuits steer probability without measuring too early. The basic single qubit gates provide a useful vocabulary. The X gate is often compared with a classical NOT operation because it exchanges the computational basis states 0 and 1. Applied to a qubit known to be 0, it produces 1, and applied to 1, it produces 0. Yet its action is broader than a classical bit flip because it must also transform arbitrary superpositions consistently. On the Bloch sphere, the X gate can be pictured as a rotation that carries the state through half a turn around one axis. The Y and Z gates are related transformations around other axes, and their importance becomes clearer once phase is included. The Z gate, for example, leaves the measurement probabilities of the basis states unchanged while reversing the relative phase of one component. A qubit can therefore look exactly the same if measured immediately in the computational basis, and yet behave differently after another gate allows that phase change to interfere with other amplitudes. The Hadamard gate has a different role. It is commonly used to move between a basis state and an equal superposition. Applied to 0, it produces a balanced combination of 0 and 1. Applied again under ideal conditions, it reverses that transformation and returns the state to 0. This simple sequence reveals an important property of quantum gates. The intended operation is not random. It reshapes amplitudes in a precise and reversible way. The Hadamard gate is therefore not a device that merely makes a qubit uncertain. It changes the basis in which information is expressed, allowing later operations to turn phase differences into measurable consequences. More general single qubit control is often described with rotation gates. Instead of making one fixed transformation, these gates rotate the state by a chosen angle around a particular axis of the Bloch sphere. By combining rotations, a processor can approximate or implement a wide range of single qubit transformations. At the mathematical level, the ideal operations share a crucial property: they are unitary. A unitary transformation preserves the normalization of the quantum state and is reversible. If an ideal gate transforms one state into another, an inverse operation exists that can recover the original state. This reversibility distinguishes the core evolution of an isolated quantum circuit from many familiar classical operations. A classical gate, such as an ordinary two-input operation, can erase information about its inputs, because several different input combinations can produce the same output. An ideal quantum gate cannot simply collapse distinct input states into one identical state while preserving quantum information. The transformation must retain enough structure that the process can in principle be undone. Measurement is different because it is not treated as an ordinary reversible gate in the same way. This separation between reversible evolution and measurement shapes the architecture of quantum algorithms. Single qubit gates alone cannot produce every form of quantum computation. To create useful correlations between qubits, the circuit also needs operations that act jointly on more than one qubit. The controlled NOT gate is one of the standard examples. It uses one qubit as control and another as a target. In the computational basis, the target is flipped when the control is 1 and left unchanged when the control is 0. If the control qubit is itself in superposition, the gate acts coherently on all components of the joint state. A branch associated with control 0 leaves the target alone, while a branch associated with control 1 flips it. When the input has the appropriate form, the output becomes entangled. This makes controlled gates one of the main bridges between local qubit manipulation and the shared states needed by larger algorithms. Other controlled operations can apply phase shifts or rotations conditionally, and more complicated circuits build from the same principle. One part of the quantum state changes only when another part satisfies a specified condition. The word condition should not be interpreted as a hidden classical decision made during the gate. No measurement has to occur. The control relationship is encoded directly into the unitary transformation of the joint state. This ability to preserve coherence while coupling qubits is essential. Measuring the control first and then applying a classical instruction to the target would generally destroy the superposition and remove the entanglement that the algorithm may require. Quantum control keeps the alternatives coherent. A complete quantum circuit is formed by arranging such gates in a deliberate sequence. The circuit usually begins with qubits prepared in known states, often the computational 0 state. Single qubit gates create the required superpositions or phases. Multi-qubit gates establish correlations and entanglement. Further rotations and controlled operations reshape amplitudes so that interference develops in the intended way. Only near the end or at carefully selected intermediate points in some architectures are measurements introduced to convert quantum information into classical outcomes. The circuit diagram therefore represents more than a chain of instructions. It is a map of how the state vector is supposed to evolve. Each gate changes the geometry and phase structure of that state, while the sequence as a whole attempts to move probability toward outcomes that reveal something about the problem. Because ideal quantum evolution is reversible circuits often include steps that deliberately undo earlier calculations. A quantum algorithm can compute an intermediate quantity, use it to alter a phase or create a conditional effect, and then reverse the temporary computation so that auxiliary qubits return to their original states. This process is often called uncomputation. Reversibility therefore becomes a practical design tool rather than a mathematical curiosity. It allows an algorithm to borrow workspace and then erase the evidence of the workspace without performing an ordinary irreversible deletion. The gates used in a conceptual algorithm are not always the same gates executed directly by hardware. A high-level circuit may describe a convenient operation, while the processor supports a smaller native gate set determined by its physical design. A compiler then decomposes the desired circuit into operations the machine can actually perform. Circuit depth, meaning how many sequential layers of operations must occur, becomes especially important when qubits have limited coherence. A theoretically elegant algorithm can fail experimentally if its circuit remains active longer than the hardware can preserve the required state. Connativity creates another constraint. A circuit diagram may draw a controlled gate between any two logical qubits, but a physical processor may permit direct interaction only between certain pairs. If two distant qubits need to interact, the compiler may have to move their quantum states through a sequence of swap operations, or use a hardware-specific method to mediate the interaction. High-quality quantum control depends on this balance. Each gate must be accurate, coherent, and selective. A pulse that is slightly too long can over-rotate a qubit. A frequency error can shift a phase. Crosstalk can disturb a nearby qubit that was meant to remain untouched. An imperfect entangling gate can introduce correlated errors that become difficult to correct later. The circuit model assumes exact unitary operations, but a real processor only approximates them. This gap between ideal gates and physical gates is one of the central reasons quantum computing remains difficult to scale. The mathematics allows a long circuit to be described cleanly. The hardware must reproduce every transformation closely enough that the final interference pattern survives. Quantum gates are therefore where theory meets control. They provide the language for rotating one qubit, linking several qubits encoding phase, creating entanglement and reversing temporary calculations. Their power comes not from any single gate, but from composition, because simple reversible transformations can be combined into circuits capable of expressing far richer quantum operations. Yet every gate also spends part of the machine's limited error budget. The more elaborate the circuit becomes, the more carefully its operations must be chosen, scheduled, and protected. Once the gates have shaped the state into the desired pattern, the computation reaches a boundary that no unitary transformation can cross on its own. The amplitudes still exist as quantum information, but the outside world needs a classical result, and obtaining that result requires measurement. Measurement is the boundary where a quantum computation stops being purely quantum and begins to produce information that can be handled by an ordinary computer. Until that point, the state of the qubits is described through amplitudes, phases, and correlations that evolve under quantum gates. None of those quantities can simply be opened and read as though they were entries in a conventional memory register. A measurement asks a specific physical question of the quantum system and returns a classical result. In the computational basis, measuring one qubit produces either 0 or 1. Measuring several qubits produces a classical bit string, assembled from those individual outcomes. What appears simple at the output is therefore the end of a process whose internal description may have involved an enormous number of amplitudes. The connection between the two is probabilistic. If a qubit is described by amplitudes associated with 0 and 1, the probability of obtaining either outcome is determined by the squared magnitude of the corresponding amplitude. This relationship is known as the Born rule. It is one of the basic bridges between the mathematical state and observable experimental results. The amplitudes themselves can be complex and can carry phase information, but the probability obtained in a particular measurement basis depends on magnitude squared. For a properly normalized single qubit, the probabilities of 0 and 1 add to 1. A state weighted heavily towards 0 will produce 0 in most repeated measurements, while a balanced superposition will produce roughly equal numbers of 0 and 1 when measured many times in the same basis. One run, however, reveals almost nothing about that distribution. If a balanced qubit is measured once, and the result happens to be 0, the result does not show that the original state was definitely 0. The same observed outcome could have come from many different quantum states. This is why quantum circuits are usually executed repeatedly. Each execution begins with a fresh preparation of the qubits, applies the same sequence of gates, and performs the same measurement. By collecting many outcomes, the experiment can estimate the underlying probability distribution. The repeated executions are often called shots. A circuit producing 0 about half the time and 1 about half the time begins to reveal a statistical pattern, but the estimate remains subject to ordinary sampling uncertainty. More repetitions provide a more precise picture of the probabilities, assuming the hardware itself remains stable. This repeated sampling is not an accidental limitation of present machines. It follows from the nature of quantum measurement. A single copy of an unknown quantum state does not reveal all of its amplitudes. The result is a sample from a distribution defined by the state and the chosen basis. That chosen basis matters, The computational basis is only one way to measure a qubit, a quantum state that produces equal probabilities for zero, and one in that basis may produce a completely predictable result in another basis. This is how phase information invisible to one direct measurement can become observable. Instead of attempting to measure phase directly as a separate hidden variable, a circuit can rotate the state before measurement. The rotation changes the relationship between the state and the measurement basis, converting phase differences into different outcome probabilities. In practice, many quantum experiments therefore place additional gates immediately before measurement. Those gates do not alter what occurred earlier in the computation. They change the perspective from which the final state is interrogated. This idea is essential for reconstructing more complete information about a qubit, or testing whether a desired quantum state was prepared. Measurement also changes the state. In the simplest projective description, measuring a qubit in the computational basis produces one of the basis outcomes, and after that measurement the qubit is associated with the observed state, rather than with the original coherent superposition. The phase relationships that existed between the measured alternatives are no longer available in the same way for later interference. This is why an algorithm cannot repeatedly inspect its intermediate state without consequence. A classical program can examine a variable copy, record it, and continue while leaving that variable intact. Quantum computation does not generally permit the same style of observation. Reading an unknown quantum state can disturb the very structure the algorithm is attempting to preserve. As a result, quantum circuits are often designed so that the essential interference occurs before the main measurement stage. There are important architectures and algorithms that use intermediate measurements, but those measurements are inserted deliberately with the resulting classical information incorporated into the remaining control logic. Measurement is therefore not forbidden during a quantum computation. It is simply not passive. Every measurement has to be understood as part of the algorithm. The contrast becomes especially important in entangled systems. If two qubits share an entangled state, measuring one can change the conditional description of the other. Consider a pair arranged so that measurements in the computational basis always agree. Before either qubit is measured, the joint system is described by one entangled state. Once one measurement produces zero, later measurement of the partner in the same basis will also produce zero in the ideal case. If the first result is 1, the partner will correspondingly return 1. Yet the first local outcome remains random. Nothing about the measurement allows the experimenter to choose which correlated result appears. The measurement reveals one branch of the joint probability structure while preserving the statistical correlations predicted by the entangled state. This again shows why measurement cannot be treated merely as reading a hidden classical value that existed all along. The basis chosen for measurement affects which correlations can be observed, and different measurement choices can reveal patterns that no simple model of predetermined local values can reproduce. In a quantum computer, measurement has an additional practical layer because physical detectors are imperfect. A qubit may be in the state corresponding to 0 while the measurement electronics report 1 or the reverse. These readout errors are different from gate errors and from decoherence, although all of them contribute to the reliability of a computation. Experimental systems therefore characterize measurement fidelity and often use calibration procedures to estimate how frequently one outcome is mistaken for another. The final histogram displayed by a quantum programming system is not a direct photograph of an ideal quantum state. It is a collection of classical counts produced by repeated physical preparation control and readout, all of which may contain imperfections. Distinguishing the intended probability distribution from hardware noise becomes increasingly important when differences between outcomes are small. Measurement also explains why the enormous quantum state space cannot be treated as an enormous classical memory. A register of many qubits may require a vast number of amplitudes for its mathematical description. but a single measurement does not release that entire description. It returns one bit string. Repeating the experiment reveals selected statistical features, but extracting every amplitude of a general large state would itself require an impractical amount of data. Quantum algorithms must work around this limitation rather than defeat it. They are designed so that the useful property of the computation becomes compressed into a measurement distribution that can be estimated efficiently. Sometimes the desired information appears as one outcome with unusually high probability. Sometimes it appears as a pattern across many possible bit strings. Sometimes the quantum measurements provide values that must be fed into a classical algorithm for further processing. The quantum and classical parts are therefore often intertwined. The processor prepares and transforms a state that would be difficult to reproduce classically. Measurement converts part of that state into ordinary data, and a classical computer interprets the data, updates parameters, checks conditions, or performs arithmetic that does not benefit from being quantum. This hybrid structure is not a temporary compromise caused only by immature hardware. It follows naturally from the fact that quantum computation begins with classical problem descriptions and must eventually produce classical information that can be used outside the processor. Measurement is the narrow channel through which that information emerges. Its narrowness explains why quantum algorithms must be designed backward from what can actually be observed. It is not enough to create an interesting state somewhere inside the circuit. The computation must arrange that state so that measurement reveals a relevant feature with useful probability and manageable statistical cost. In this sense, measurement places a discipline on every earlier step. Superposition must be structured. Entanglement must serve a purpose. Interference must redirect amplitudes. Gates must bring the state into a form whose classical samples answer a meaningful question. Only then can repeated runs accumulate into evidence rather than noise. The complete shape of a quantum algorithm therefore becomes visible at this boundary. Preparation creates a controlled starting point. Quantum evolution encodes and transforms information. Interference concentrates what matters. Measurement produces samples, and classical processing turns those samples into an answer. The next stage is to follow that entire sequence as one continuous computational process. A quantum algorithm is not a single moment of quantum behavior, but a carefully arranged sequence in which preparation-controlled evolution, interference measurement, and classical interpretation all serve one another. The process usually begins in a state that is deliberately simple. Physical qubits are prepared as reliably as possible, often close to the computational zero state, so that the circuit starts from a known reference, rather than from uncontrolled uncertainty. This initial simplicity matters because every later transformation assumes something about what came before it. If preparation is unreliable, the circuit may manipulate the wrong state with perfect precision and still produce the wrong distribution at the end. State preparation therefore belongs to the algorithmic story, even though it can appear almost invisible in a diagram. From that starting point, gates create the structure needed by the problem. Some qubits may be rotated into superpositions. Others may remain in definite basis states until they are needed. Controlled operations may entangle selected parts of the register. Phase shifts may encode information that has no immediate effect on computational basis measurement, but becomes important later when amplitudes are recombined. The sequence is rarely arbitrary. Each stage is designed to change the geometry of the state in a way that prepares the next stage to reveal something useful. The central difficulty is that quantum information cannot generally be inspected along the way without disturbing it. In a classical algorithm, an intermediate value can be printed, copied, stored, or examined while the computation continues. A quantum algorithm must often carry its intermediate structure forward without measuring it, because the phase relationships and entanglement created early in the circuit may be needed much later. This makes quantum algorithm design unusually dependent on foresight. The circuit has to be constructed so that hidden information accumulated inside amplitudes eventually becomes accessible through interference. Superposition often enters near the beginning because it allows a register to occupy a coherent combination of many basis states. Yet creating that combination is not the goal. A uniform superposition over a large number of candidates can be easy to prepare and almost useless by itself. The algorithm must then imprint some feature of the problem onto the state. This can be done in several ways. A function may be evaluated coherently so that different basis components become correlated with different outputs. A chosen property may be encoded as a phase change. A Hamiltonian, which describes the energy structure of a quantum system, may be allowed to govern evolution for a controlled period. In other algorithms, a register may be entangled with an auxiliary system, so that information about one quantity is transferred into another part of the state. The specific mechanism changes from problem to problem, but the general purpose is consistent. The circuit must cause relevant structure in the input problem to become structure in the amplitudes or phases of the quantum state. Once that information has been encoded, interference becomes the tool that turns hidden structure into observable bias. The circuit applies transformations that mix components together, allowing amplitudes associated with different computational pathways to reinforce or cancel. This is often where the apparent advantage of the quantum algorithm is created. The machine does not simply carry every candidate answer forward unchanged. It uses the relationships among those candidates. A successful design arranges the state so that the important global feature of the problem affects many amplitudes coherently, and then converts that distributed effect into a relatively small set of measurement statistics. This is why many quantum algorithms are easier to understand when viewed backward from the measurement. The useful question is not merely what state can be created, but what final distribution would expose the desired property. Once that target distribution is identified, the earlier gates can be chosen to build the phase and correlation structure required to produce it. Measurement then performs the transition from the quantum register to classical data. A single circuit execution usually yields only one outcome, so the algorithm may need many repetitions. The resulting collection of bit strings, estimated expectation values or sampled quantities, is rarely the entire answer by itself. Classical post-processing often follows. In some algorithms, the measured result becomes input to ordinary arithmetic. In others, it is checked against a condition, and the quantum circuit is run again. A classical optimizer may update parameters between quantum executions. Statistical analysis may estimate an average from repeated measurements. Number-theoretic routines may interpret measured values that encode an approximate period or phase. The boundary between quantum and classical computation is therefore not a line separating two unrelated machines. It is often a loop in which each side performs the work for which it is best suited. This hybrid structure is especially visible in variational algorithms. A quantum processor prepares a parameterized state and measures a quantity of interest. A classical algorithm receives that measurement estimate, adjusts the parameters, and sends new values back to the quantum processor. The cycle repeats in an attempt to move toward a lower energy, a better approximation, or another objective. Such methods became prominent partly because they can use relatively short circuits, which is attractive on noisy hardware. Their practical value, however, depends on many details, including whether the optimization landscape can be navigated efficiently, whether measurement requirements become too large, and whether a comparable classical method performs just as well. The existence of a quantum subroutine does not by itself guarantee an advantage. The entire end-to-end cost has to be considered. This broader accounting is one of the most important principles in evaluating quantum algorithms. A procedure may contain a quantum step that is mathematically efficient while relying on state preparation data, loading error correction, or repeated sampling that consumes substantial resources. The comparison with classical computing must include those costs rather than isolating only the most elegant part of the circuit. In some theoretical algorithms, the speedup is expressed in how the required number of operations scales as the problem grows. That asymptotic improvement can be profound even if small instances remain easier on classical hardware. In other cases, the formal quantum subroutine assumes access to an idealized oracle, or to quantum data that may be expensive to prepare in practice. These assumptions do not make the algorithms meaningless, but they define the conditions under which the claimed improvement applies. Designing a useful quantum algorithm therefore involves more than translating classical instructions into quantum gates. Direct translation usually misses the point. If a classical method examines candidate solutions one by one, placing those candidates into superposition and reproducing the same logic coherently does not automatically create a large speedup. The quantum method needs a structure that can exploit interference. It may use symmetry, periodicity, spectral properties, algebraic relationships, or the natural dynamics of a quantum system. The advantage comes from reorganizing the computation around something quantum mechanics handles differently, not from performing an ordinary algorithm on unusual hardware. This is why known quantum speedups tend to be closely connected to specific mathematical structures. Period finding supports Shor's algorithm. Amplitude amplification supports Grover's algorithm. Phase estimation can extract eigenvalue information from controlled quantum evolution. Quantum simulation uses the fact that one quantum system can under suitable control reproduce the evolution of another. These examples look different on the surface, but each constructs a route from an inaccessible global property to a measurable statistical signature. Error also changes the design. A circuit that works perfectly on paper may require too many operations for a real device to execute reliably. Each additional gate creates another opportunity for phase errors, unwanted coupling relaxation, or readout problems to affect the result. A practical algorithm must therefore be judged together with the machine that runs it. Circuit depth, qubit connectivity, gate fidelity measurement cost, and the overhead of error correction can all determine whether the algorithm remains useful outside an ideal mathematical model. This has encouraged research into circuits that accomplish the same logical task with fewer operations, alternative decompositions adapted to particular hardware and methods that divide work between quantum and classical processors. The difficulty grows because increasing the number of qubits does not automatically make algorithm design easier. A larger register offers a larger state space but also more possible errors, more interactions to control, and more ways for the system to accumulate unwanted correlations. Useful algorithms must convert scale into structure. They need not only enough qubits, but enough high-quality operations performed in the right order before coherence is lost. At its most compact, the pattern of a quantum algorithm is therefore simple to state and difficult to execute. The machine begins from a controlled state, creates superposition or entanglement, where those resources serve the problem, encodes meaningful information into amplitudes and phases, engineers interference so that selected features become statistically visible, performs measurement and hands the result to classical computation for interpretation or further iteration. Every stage constrains the others. Preparation determines what can be trusted. Gates determine what structure is created. Interference determines what can become prominent. Measurement determines what can actually be observed. Classical processing determines whether those observations become a usable answer. The challenge is not merely to make a circuit quantum. It is to make the quantum part perform work that changes the complexity or quality of the solution enough to justify everything required around it. The clearest evidence that this can happen comes from a small group of algorithms that changed expectations for the entire field because they showed in precise mathematical terms that quantum computation could outperform known classical approaches on particular problems rather than merely behave differently. The algorithms that made quantum computing famous did not all promise the same kind of advantage. Each one exploits a different mathematical structure, and together they reveal why quantum computation is both powerful and sharply limited. Shor's algorithm is the clearest example of a result that changed the strategic importance of the field. It provides an efficient quantum method for factoring large integers and for solving discrete logarithm problems, two mathematical tasks that are closely connected to several widely used forms of public key cryptography. The importance of the algorithm is not that quantum computers suddenly become better at every arithmetic problem. It is that certain cryptographic systems derive their security from the apparent difficulty of solving particular mathematical problems on classical computers when the numbers involved are large enough. If a sufficiently large fault-tolerant quantum computer could run Shor's algorithm at the required scale, that assumption would no longer provide the same protection. The algorithm achieves its advantage by reformulating factoring so that the quantum processor searches for a hidden period rather than directly testing possible factors one after another. Periodicity is a form of global mathematical structure, and quantum mechanics provides a way to encode that structure into phase relationships across a superposition. The circuit prepares many possible inputs, coherently applies an operation related to modular arithmetic, and uses interference to make information about the period visible in the measurement statistics. A quantum Fourier transform plays a central role by reorganizing amplitudes so that values consistent with the hidden periodicity become more likely to appear. The measurement still does not simply return the factors. It yields information from which classical number theory can recover the period with some probability, and from that period the factors may be derived. Several runs may be needed, and not every measured result is useful. The algorithm is therefore a hybrid process in which quantum interference extracts a structure that is difficult to uncover classically, while classical computation completes the final arithmetic. What makes Shor's algorithm remarkable is the scaling of the ideal algorithm rather than a claim that present quantum hardware can already factor cryptographically significant numbers. Large, useful implementations would require many reliable logical operations and error-corrected qubits. The theoretical consequence is nevertheless profound, because it demonstrates that a problem believed to be difficult for classical computation can belong to a very different complexity regime on a quantum computer. Grover's algorithm illustrates a more modest but much broader type of improvement. It addresses unstructured search in an oracle model. Suppose there is a collection of possible candidates and a procedure capable of recognizing whether a chosen candidate is the desired one. A straightforward classical strategy may need to examine a number of candidates proportional to the size of the search space. Grover's algorithm reduces the required number of oracle queries so that it grows approximately with the square root of that size. The improvement is not exponential, and this distinction matters. A quantum computer running Grover's algorithm does not make an enormous search space disappear. As the problem grows, the required work still increases. It simply increases more slowly than in the corresponding classical query model. The mechanism is amplitude amplification. The register begins in a superposition over possible candidates. An oracle marks the desired state through a phase change rather than by printing an answer. Another operation then redistributes amplitudes around their average, increasing the amplitude of the marked state while decreasing the others. Repeating this pair of transformations rotates the state toward the target. After approximately the appropriate number of repetitions, measurement has a high probability of returning the desired candidate. Continuing indefinitely would not help because the state would eventually rotate past the point of maximum success probability. Grover's algorithm therefore exposes the precision required by quantum interference. The computation must know not only what transformation to perform, but roughly how long to perform it. Its square root improvement is also a useful reminder that quantum advantage comes in degrees. Some problems receive dramatic theoretical speed-ups. Others receive polynomial improvements. Some receive no known useful improvement at all. Quantum phase estimation represents another foundational pattern. Instead of searching directly through candidate solutions, it extracts information about a phase associated with the action of a unitary operation on a special state. If that state is an eigenstate of the operation, applying the operation changes the state by a phase factor, rather than by altering its essential direction in state space. Phase estimation converts that hidden phase into a measurable binary approximation. It typically uses a control register placed into superposition, controlled applications of increasing powers of the unitary operation, and an inverse quantum Fourier transform that translates relative phase into measurement probabilities. The procedure matters because many physical and mathematical quantities can be related to eigenvalues. In quantum mechanics, energy levels of a system correspond to eigenvalues of its Hamiltonian. If controlled time evolution under that Hamiltonian can be implemented, and an appropriate input state can be prepared, phase estimation can provide information about those energies. The algorithm is therefore not merely a technical subroutine. It connects quantum computation to the spectral structure of physical systems. It also appears inside larger algorithms, including approaches to quantum simulation and several historically important proposals in quantum chemistry. Its usefulness depends strongly on the ability to perform coherent controlled operations with high precision and often for substantial circuit depth, which makes large-scale implementations demanding on noisy hardware. Quantum simulation takes the connection to physics even further. Long before practical quantum computers existed, one of the central motivations for building them was the difficulty classical computers face when simulating general quantum systems. A many-particle quantum state can require a number of amplitudes that grows exponentially with the number of components when represented without exploitable simplifications. Classical numerical methods can handle many important systems through approximations, symmetries, specialized representations, or limited interaction structures, but difficult cases remain. A quantum computer does not remove every complication, yet it begins with a state space governed by the same broad mathematical framework as the systems being modeled. That creates the possibility of representing and evolving certain quantum systems more naturally. A quantum simulation algorithm can map the degrees of freedom of a molecule material or model Hamiltonian onto qubits approximate the desired time evolution or energy structure using quantum gates, and then measure selected properties. The final goal is not to recover the entire quantum wave function as a classical list. Doing so would generally destroy the advantage by requiring an enormous amount of output. Instead, the algorithm targets particular observable quantities such as energies, correlations, transition properties, or dynamical behavior. This same limitation that appeared earlier in measurement becomes a design principle. The quantum state may be extremely rich, but the useful calculation must ask a question whose answer can be extracted efficiently. These famous algorithms also expose a common misunderstanding about speed. There is no known universal quantum procedure that takes an arbitrary classical program and makes it dramatically faster. Shor's algorithm succeeds because factoring and discrete logarithms contain mathematical structures that can be connected to period finding. Grover's algorithm succeeds because amplitude amplification can reduce the query complexity of unstructured search, but only by a square root factor. Phase estimation succeeds when the relevant information is encoded in the eigenphase of a unitary process that can itself be implemented efficiently. Quantum simulation is promising because the problem being modelled is quantum mechanical from the beginning. In each case, the advantage comes from alignment between the structure of the problem and the operations available to a quantum computer. If that alignment is absent, superposition and entanglement do not manufacture an advantage by themselves. There is another distinction hidden inside these examples. Theoretical speed-up describes how the resources of an ideal algorithm scale compared with an appropriate classical method under stated assumptions. It does not automatically imply that the quantum method is faster for every practical problem size. A quantum circuit may require expensive error correction, complex state preparation, large numbers of gates or repeated measurements. Classical algorithms may also improve changing the point at which a quantum approach becomes competitive. The meaningful comparison therefore includes the complete workload, rather than only the most elegant quantum subroutine. This is especially important when an algorithm is described using an oracle. The cost of implementing that oracle physically may be substantial, and any practical advantage depends on including that cost. The early landmark algorithms remain important precisely because they do more than demonstrate unusual quantum behavior. They provide exact examples of computational tasks for which quantum mechanics changes the available strategy. Shor shows that hidden periodic structure can transform the difficulty of number-theoretic problems. Grover shows that interference can produce a general but limited improvement even when little structure is available. Phase estimation shows how relative phase can become a numerical answer. Quantum simulation shows why a controllable quantum system may be especially well suited to studying another quantum system. Together they replace the vague idea of universal quantum speed with a more precise picture. Quantum advantage is algorithmic, conditional, and problem-dependent. The next question is therefore no longer whether the mathematics permit such advantages. It is whether physical machines can preserve enough coherence, execute enough accurate gates, and connect enough qubits to run these ideas at scales where their theoretical promise becomes useful. A quantum computer becomes real only when the abstract idea of a qubit is tied to a physical system that can be prepared, controlled, coupled, protected, and measured with extraordinary precision. There is no single substance called a quantum computing material, and no universal particle that serves as the one true qubit. A qubit is a role played by a carefully selected pair of quantum states, and many different physical systems can be engineered to play that role. This is why quantum computing hardware has developed along several paths, rather than converging immediately on one design. Superconducting circuits, trapped ions, neutral atoms, photons, spins, and other experimental platforms all attempt to solve the same basic problem in different ways. Each must create a stable two-level quantum system, manipulate its state through controlled operations, connect it to other qubits when entanglement is required, and finally produce a measurement result that can be interpreted classically. The difficulty is that qualities desirable in one part of this process can work against qualities needed elsewhere. A qubit that is extremely well isolated may preserve coherence for a long time, but be difficult to control quickly. A qubit that interacts strongly with its surroundings may be easy to manipulate but lose its quantum state more readily. A platform with excellent local operations may have limited connectivity between distant qubits. Another may offer flexible interactions but require slower gate sequences or more complex control. Hardware design therefore becomes an exercise in balancing competing demands rather than maximizing one simple number. Superconducting qubits are among the best-known examples of engineered quantum systems. Instead of relying on a naturally occurring atom alone, they use electrical circuits cooled to extremely low temperatures until certain collective behaviors become quantum mechanical. The circuit is designed so that two energy states can serve as the logical basis of a qubit. Microwave control signals can then rotate the qubit state or help create interactions between neighboring qubits. The attraction of this approach lies partly in engineering. Circuits can be fabricated using techniques related to those developed for modern electronics, and control operations can be performed relatively quickly. Yet superconducting systems also bring difficult requirements. They must operate in highly controlled cryogenic environments. Their quantum states remain sensitive to imperfections and noise, and scaling. The number of qubits means scaling an increasingly complicated network of control lines. Couplers read out components and calibration procedures. A processor cannot simply add more circuits and expect the resulting machine to remain equally precise. Every additional element changes the environment in which the others operate. Trapped ion systems begin from a very different physical picture. Here the qubits are encoded in internal states of electrically charged atoms confined by electromagnetic fields. Because atoms of the same species are naturally identical, trapped ions offer a degree of uniformity that engineered solid-state devices must work to reproduce. Laser or electromagnetic control can manipulate individual ions, and shared motion within the trap can mediate entangling operations between them. These systems can support highly accurate control, but their trade-offs differ from those of superconducting circuits. Operations may proceed on different timescales, and maintaining precise control over a growing collection of ions introduces challenges in optical access, trapping geometry, motion, and system complexity. The central question is not whether one platform has perfect qubits and another has poor ones. It is how each platform converts its physical strengths into a scalable architecture while managing its characteristic sources of error. Neutral atom approaches again rearrange the balance. Instead of using charged particles held in an ion trap, they use electrically neutral atoms positioned and controlled through carefully shaped light fields. Arrays of atoms can be organized into flexible geometries, and selected interactions can be activated to perform quantum operations. This can make connectivity patterns attractive for certain types of circuits, because the physical arrangement of the atoms can be designed around the intended computation. The same platform, however, must still solve the universal quantum engineering problems of preparation, control, coherence, measurement, and reproducibility. Large arrays are useful only if the individual elements can be loaded, positioned, manipulated, and read with sufficiently high reliability. As with every platform, qubit count without dependable operations is only part of the story. Photonic approaches use particles of light as carriers of quantum information. Their appeal comes from a property that is immediately useful for communication. Photons can travel through optical systems and can preserve quantum information while moving over distances that would be difficult for many stationary qubits. This makes photonic ideas especially important wherever computation and quantum networking begin to overlap. Yet light also behaves differently from matter when interactions are required. Quantum computation needs not only isolated qubits, but controlled relationships between them. A successful photonic architecture must therefore create, route, manipulate, interfere, and detect photons with enough precision to implement the desired logical operations. Loss becomes a major concern because a missing photon can mean missing quantum information. Once again, the apparent strength of the physical system shapes the form of the engineering challenge rather than eliminating it. Spin qubits provide another route. Quantum information can be associated with spin-like degrees of freedom in carefully controlled microscopic systems. These approaches are attractive partly because spin states can sometimes be integrated with extremely small device structures, raising the possibility of dense quantum hardware. But density alone is not the same as scalability. The qubits still require reliable initialization, coherent control, suitable coupling, high-quality measurement, and enough uniformity that a large processor does not become impossible to calibrate. Every physical realization, therefore, has to answer the same set of questions in its own language. How accurately can a gate be performed? How long does the state remain coherent? Which qubits can interact directly? How quickly can those interactions occur? How easily can the device be fabricated or assembled at larger scale? How much infrastructure is required around each qubit? How consistently can the system be calibrated from one operating cycle to another? These questions explain why comparing quantum processors by qubit number alone can be misleading. A processor with fewer qubits but higher fidelity may be able to execute deeper and more reliable circuits. Another with more qubits may offer a larger state space but accumulate errors too rapidly for complex algorithms. Connectivity matters because poor connectivity can force a circuit to use extra gates simply to bring quantum information into the right arrangement. Gate speed matters because a circuit must often finish before decoherence destroys the state. Measurement quality matters because a perfectly prepared computation is still useless if the final readout frequently reports the wrong result. Scalability matters because a design that performs beautifully with a small number of qubits may become unmanageable when the control system grows much larger. These trade-offs make it difficult to declare one hardware platform the inevitable winner. Different architectures may prove better suited to different roles. Some may favor fast local processing. Some may excel in precise operations. Some may offer flexible connectivity or easier physical transport of quantum information. Future systems may even combine technologies rather than relying on a single physical mechanism, from preparation to communication to long-term storage. The abstract circuit model hides these differences because the mathematics treats a qubit as a qubit and a gate as a gate. Physical hardware cannot hide them. The same logical operation may require completely different laboratory techniques depending on the platform. A rotation represented by one symbol in a circuit diagram might correspond to a microwave pulse in one machine, an optical operation in another, or a different controlled interaction elsewhere. An entangling gate that appears identical at the algorithmic level may depend on a fabricated coupler shared particle motion, an atomic interaction, or interference between photons. The software description is intentionally universal. The hardware beneath it is not. This gap between logical abstraction and physical implementation is one of the defining realities of quantum engineering. It allows researchers to develop algorithms without committing every idea to one device, but it also means that practical performance depends heavily on how efficiently an abstract circuit can be translated into the native operations of a particular machine. Building a quantum computer is therefore not the search for one perfect quantum object. It is the search for a complete physical architecture in which preparation, coherence, interaction, control measurement, and scaling can all remain good enough at the same time. Each platform offers a different compromise, and no compromise has yet removed the central difficulty. Quantum information must be exposed enough to be manipulated and protected enough to survive. That tension becomes sharper as machines grow because every added qubit creates new opportunities for unwanted interactions and new paths through which information can leak into the environment. The next challenge is therefore not simply how to build more qubits, but how to keep increasingly large collections of them from losing the delicate quantum structure that makes computation possible at all. Decoherence begins when a quantum system that was meant to evolve under carefully controlled operations becomes entangled with things that are not part of the computation. A stray electromagnetic field, a vibration, thermal motion, an imperfect control pulse, a material defect, or an unwanted interaction with a neighboring qubit can all disturb the state. The effect is not always as simple as flipping 0 into 1. Quantum information also depends on phase relationships. and those relationships can be degraded even when a direct measurement of the qubit still appears plausible. This is what makes quantum noise especially damaging. A classical computer can tolerate a certain amount of physical imperfection because its logical states are engineered to be separated by large margins. A small voltage fluctuation does not usually turn a classical 0 into a 1. Quantum hardware operates differently. The information may be stored in amplitudes and phases that must remain coherent over many successive operations, so errors that seem physically small can accumulate into a large computational failure. Decoherence is the broad name given to the loss of controlled quantum coherence through interaction with the environment. If a qubit begins in a well-defined superposition, the relative phase between its components can remain predictable only while the system is sufficiently isolated from uncontrolled influences. Once the environment begins to acquire information about the qubit even indirectly, the coherent relationship can weaken. From the perspective of the processor, the quantum state starts losing the interference structure on which later gates depend. This does not require a human observer or a deliberate measurement device. The surrounding world can effectively act as a measuring environment simply by becoming correlated with the qubit. Information that was once confined to the computational system spreads outward into microscopic degrees of freedom that are not tracked or controlled. The result is that the qubit behaves less like an ideal coherent quantum system and more like a statistical mixture. Different physical platforms experience this process through different mechanisms, but the computational consequence is similar. The state no longer follows the exact evolution assumed by the algorithm. One important form of decoherence involves energy relaxation. A qubit prepared in a higher energy state may gradually release energy into its surroundings and fall toward a lower energy state. Another form involves dephasing, where the relative phase between components of a superposition becomes uncertain even without a full energy transition. These two effects damage quantum information in different ways. Relaxation can change the populations associated with basis states. Dephasing can leave those populations apparently unchanged while destroying the phase relation needed for later interference. A measurement performed immediately in one basis might fail to reveal that anything went wrong, yet a later gate that depends on coherent recombination can produce the wrong distribution. This delayed visibility makes quantum error diagnosis difficult. A circuit may contain an error long before the final result reveals it. Gate errors add another layer. An ideal quantum gate performs an exact unitary transformation, but a physical gate is implemented by finite control signals applied to imperfect hardware. A microwave pulse may rotate a superconducting qubit by slightly the wrong amount. A laser pulse may have imperfect timing or intensity. An entangling operation may leave behind a phase shift that was not intended. Small deviations can accumulate as a circuit becomes deeper. If one operation introduces a tiny error and the next operation assumes the state is exact, the mistake can be transformed into something more complicated. Quantum circuits therefore depend not only on whether gates work on average, but on how consistently and predictably their errors behave. Some errors fluctuate randomly, others are systematic and may repeat in the same direction until calibration corrects them. Still others become correlated across several qubits, making them harder to model as independent failures. State preparation introduces error before the main computation has even begun. A circuit may assume that every qubit starts in the zero state, but real initialization is not perfect. A small fraction may begin in the wrong state, or in a state that does not match the intended basis preparation closely enough. The entire circuit then evolves from an incorrect starting condition. Measurement brings its own failures at the opposite end. A qubit that truly occupies a state associated with zero may be reported as 1 or the reverse. Readout electronics must distinguish physical signals that are not infinitely separated, and noise can make the distinction imperfect. Preparation and measurement errors can sometimes be characterized through calibration experiments, but they still contribute to uncertainty in the final results. Crosstalk is another problem that becomes more serious as systems grow. A control signal intended for one qubit can disturb another. An entangling gate between one pair can shift the behavior of nearby qubits. Operations that work accurately in isolation may behave differently when many gates are executed simultaneously. This means that a large quantum processor cannot always be understood as a collection of small components whose errors simply add independently. The device is a coupled physical system, increasing density, adding control lines, and operating more qubits at once can create interactions that were negligible in smaller experiments. Scaling therefore changes the error environment itself. This is one reason raw qubit count is such an incomplete measure of progress. Adding qubits increases the size of the available state space, but it also increases the number of places where errors can appear and the number of relationships that must remain controlled. A large noisy register can become less useful than a smaller high-fidelity one if the error rate prevents meaningful circuit depth. Circuit depth is crucial because every additional layer of gates consumes time and creates further opportunities for decoherence and control error. If the quantum state cannot remain coherent long enough to execute the algorithm, then having enough qubits on paper does not solve the problem. The relevant question becomes, how many reliable operations can be performed before errors overwhelm the information? This leads to the idea of an error budget. A quantum computation can tolerate only so much accumulated imperfection before the final measurement distribution becomes too distorted to interpret. Some short experiments can be useful even when error rates are substantial, because the circuits end before much damage occurs. Large fault-tolerant algorithms demand something much harder. Errors must be detected and corrected repeatedly while the computation continues. Before reaching that stage, researchers sometimes use error mitigation techniques that attempt to estimate or reduce the influence of noise without fully correcting every quantum error. Such approaches can improve results for selected experiments, but they are not equivalent to fault-tolerant quantum error correction. Mitigation generally relies on additional measurements, calibration, extrapolation, symmetry checks, or other forms of classical analysis. Its cost can increase quickly as circuits become larger and noisier. It is therefore most useful as a tool for limited regimes rather than a complete answer to scaling. Noise also complicates the interpretation of apparent quantum advantage. If a quantum device performs a specialized calculation, the meaningful question is not merely whether the ideal circuit is difficult for a classical computer to simulate. The physical output has to remain close enough to the intended quantum distribution that the experiment still represents the target computation. As errors increase, the device may drift toward a distribution that is easier to reproduce classically or simply less useful. Demonstrating complexity therefore requires both a difficult computational task and evidence that the hardware executed it with sufficient fidelity. This again ties theory to engineering. Quantum algorithms assume coherent amplitudes and carefully controlled interference. Hardware must preserve those conditions well enough that the mathematical advantage survives contact with the laboratory. The central difficulty is that quantum computing asks the same physical system to satisfy two opposing requirements. Qubits must interact strongly enough with control equipment and neighboring qubits to perform gates, yet they must remain isolated enough from everything else to preserve coherence. They must be measurable at the end, but not accidentally measured by their environment in the middle. They must be sensitive to precisely shaped signals and insensitive to unwanted ones. Every platform attempts to find a favorable balance, but no balance eliminates noise completely. Perfect physical qubits are not the realistic goal. The deeper strategy is to make physical errors rare and structured enough that a larger encoding can detect and correct them faster than they accumulate. That shift changes the entire meaning of scalability. A useful large quantum computer may not be built from millions of nearly perfect qubits. It may be built from large numbers of imperfect physical qubits organized so carefully that they collectively behave like a much smaller number of reliable logical qubits. The path forward therefore does not require defeating quantum fragility at the level of each individual device. It requires learning how to contain that fragility through redundancy, repeated checks, and carefully designed codes. That is the threshold at which noise stops being merely something to suppress and becomes something the computation must actively diagnose and repair. Quantum error correction begins from an uncomfortable fact: the qubits used to build a quantum computer are never perfectly reliable. Yet the algorithms that promise the greatest advantages may require computations far longer and more precise than any unprotected physical qubit can sustain. The solution is not to wait for flawless hardware. It is to encode quantum information so that errors can be detected and corrected while the computation continues. This is where the distinction between a physical qubit and a logical qubit becomes essential. A physical qubit is an individual hardware element, such as a superconducting circuit, an ion, an atom, a photon, or another controlled quantum system. A logical qubit is information encoded across a larger collection of physical qubits according to a quantum error-correcting code. The purpose of that encoding is not to make the underlying hardware perfect. It is to make the combined system behave as though it were much more reliable than any one of its components. Classical error correction also uses redundancy, but quantum information creates a more difficult problem. An unknown quantum state cannot simply be copied several times and compared later because the no-cloning principle prevents perfect duplication of an arbitrary unknown state. Directly measuring the qubit to check whether it has changed is also dangerous because measurement can destroy the superposition or phase information the computation is trying to preserve. Quantum error correction therefore has to learn about errors without learning the protected quantum information itself. It accomplishes this through an indirect strategy. The logical state is distributed across several physical qubits, and additional measurements are designed to reveal patterns associated with errors rather than the value of the encoded information. These measurements produce what are called error syndromes. A syndrome does not say what the logical qubit is. Instead, it reports whether certain relationships among the physical qubits have changed in a way consistent with an error. This distinction is the foundation of the entire method. The system is repeatedly asked whether its encoded structure still obeys the constraints of the code, while the logical information remains hidden inside that structure. A simple way to understand the principle is to separate the idea of information from the idea of consistency. The logical qubit carries the information. The surrounding code defines consistency conditions that should remain true when no error has occurred. If one physical qubit experiences a bit flip-like error, a phase error, or some combination, the pattern of consistency checks can change. Measuring those checks reveals a syndrome. A classical decoder then interprets the syndrome and estimates which physical error is most likely to have occurred. The system can respond by applying a correction, or in some architectures by updating a classical record that keeps track of how future measurements should be interpreted. The crucial point is that the protected quantum state is never directly open for inspection. Only the traces left by errors are measured. Quantum errors are often described using a small set of basic error types, because more general errors can be decomposed into combinations of them. A bit flip error changes the computational basis value in a way analogous to exchanging 0 and 1. A phase error changes the relative phase between components of a superposition. Both matter because quantum information depends on both basis populations and phase relationships. A useful error-correcting code must therefore protect against more than ordinary bit flips. It must preserve the wider structure needed for interference. This is one reason quantum error correction requires more elaborate redundancy than familiar classical schemes. The code is not merely checking whether a stored symbol has changed. It is protecting a state that may never possess a definite classical value until measurement. Among the most important approaches to fault-tolerant quantum computing is the surface code. Its appeal comes from the way it organizes physical qubits into a local geometric pattern and uses repeated stabilizer measurements to detect errors. The details can become mathematically sophisticated, but the underlying idea is relatively gentle. Data qubits carry the encoded state, while neighboring measurement or ancilla qubits help test local consistency conditions. These checks are repeated again and again through time. An isolated error may change the outcomes of nearby checks, creating a pattern from which a decoder can infer where an error likely occurred. Rather than relying on one moment of perfect diagnosis, the code builds evidence from a history of syndrome measurements. Space and time become part of the error correction structure together. This repeated checking matters because the measurements themselves are not perfect. A faulty syndrome result could otherwise be mistaken for a genuine change in the data. By comparing patterns across repeated rounds, the decoder can distinguish many data errors from measurement errors and choose a correction that is statistically most plausible. The surface code is attractive partly because its checks can be arranged around local interactions, which fits the connectivity of several hardware platforms. It does not require every physical qubit to interact directly with every other one. Yet this convenience comes with substantial overhead. A single, high-quality logical qubit can require many physical qubits, especially when the physical error rate is not extremely low, or when the target logical error rate is exceptionally demanding. The exact number is not universal. It depends on the quality of the hardware, the code, distance, the error model, the decoding method, the operations required, and how reliable the overall computation must be. This is why a large quantum computer intended for fault-tolerant algorithms may need vastly more physical qubits than the number of logical qubits visible in the high-level algorithm. The difference between those two numbers is not wasted space. It is the price of reliability. The idea of code distance helps express that price. Increasing the distance of a quantum error correcting code generally means spreading the logical information across a larger structure so that more physical errors are required to produce an undetectable logical failure. A larger code can therefore suppress logical error more strongly, but only if the underlying physical operations are already good enough. This condition leads to the concept of an error correction threshold. Below the threshold, improving the code by increasing its size can reduce the logical error rate sometimes very rapidly. Above the threshold, adding more qubits and more error correction operations may fail to help, because those additional operations introduce errors faster than the code can suppress them. The threshold is not one universal number applying identically to every machine. It depends on the code, the types and correlations of errors, the available gates, the measurement process, and the architecture. Still, the principle is fundamental. Fault tolerance becomes scalable only when physical operations are sufficiently reliable that additional redundancy improves the logical system instead of making it worse. This changes the meaning of progress in quantum hardware. A machine with more physical qubits may be valuable, because it allows a larger code to be tested, but the real milestone is whether the logical qubit becomes more reliable as the code grows. If increasing the encoding size lowers the logical error rate under realistic operation, then the system begins to demonstrate the central promise of quantum error, correction. Imperfect parts can combine into a more reliable whole. Reaching that regime does not immediately produce a large universal quantum computer. Logical gates must also be performed fault-tolerantly, meaning that errors occurring during an operation should not spread uncontrollably through the encoded information. State preparation, measurement, movement of logical information, and specialized resources required by some algorithms must all be protected as well. Error correction is therefore not a protective shell added around an otherwise finished processor. It becomes part of the processor's continual operation. The machine spends much of its effort checking, decoding, and maintaining the logical state, while the useful algorithm proceeds within that protected layer. The overhead can be enormous because a long computation may require logical error rates far below the physical error rate of any individual component. If an algorithm needs a very large number of logical operations, even a small probability of failure per operation may accumulate into an unacceptable overall chance of error. The code must therefore suppress failures to a level appropriate for the full computation, not merely make one qubit look stable in a short experiment. This is why estimates for future fault-tolerant machines can involve large populations of physical qubits supporting a much smaller logical register. The scale is driven not only by how many logical qubits an algorithm needs, but also by how reliably they must operate and how many protected operations must be performed. Quantum error correction therefore offers both reassurance and a warning. It shows that fragile physical qubits do not need to become perfect before useful large-scale computation is possible. Errors can in principle be managed through encoding syndrome extraction, decoding, and repeated correction. At the same time, it reveals how demanding useful scalability really is. A processor must not only manufacture many qubits, it must control them accurately enough, measure them repeatedly, process syndrome information quickly, and maintain a code whose logical error rate continues to fall as protection increases. The future of large quantum computing rests heavily on that transition from physical qubits that merely exist to logical qubits that improve as they grow. Once that transition begins to hold experimentally, the central question changes from whether quantum information can survive at all to how much protected computation can be built on top of it. Today's quantum computers occupy an unusual place between laboratory experiment and programmable machine. They are real processors that can be accessed, controlled, and used to run increasingly sophisticated circuits, yet their capabilities remain far from the fault-tolerant systems required for the largest algorithms that first made quantum computing famous. This makes the present era difficult to summarize with a single number. Qubit count is the most visible statistic, but it is not a complete measure of computational power. A processor with many qubits may still be unable to execute a long useful circuit if its gates are too noisy, its qubits lose coherence too quickly, or its connectivity forces the compiler to insert large numbers of extra operations. A smaller machine with better control can sometimes perform a deeper or more accurate calculation. The state of quantum computing is therefore better understood through a collection of interacting limits. How many qubits can be controlled, how accurately they can be manipulated, how well they can interact, how long coherent information survives, how reliably they can be measured, and how effectively errors can be detected and suppressed. Fidelity is one of the central measures in this picture. In broad terms, fidelity describes how closely a physical operation or prepared state matches the intended ideal behavior. A gate with high fidelity produces nearly the transformation specified by the circuit. A measurement with high fidelity reports the correct outcome most of the time. A prepared state with high fidelity begins close to the state the algorithm expects. None of these quantities reaches perfection in real hardware. Even small deviations matter because quantum algorithms often rely on many operations working together coherently. If a circuit is shallow, a modest error rate may still leave a recognizable signal. If the circuit becomes much deeper, the errors can accumulate until the final probability distribution bears little resemblance to the ideal result. This is why circuit depth matters as much as raw qubit number. Depth describes how many sequential layers of operations must be completed before measurement. Gates that act on different qubits can sometimes run simultaneously, reducing the effective depth. But many algorithms still require long chains of dependent operations. Each additional layer consumes coherence time and introduces another opportunity for imperfect control. A processor may therefore have enough qubits to represent the desired state, but not enough reliable depth to complete the algorithm before noise overwhelms it. Connectivity imposes a different constraint. A logical circuit might assume that any pair of qubits can interact, while the physical machine may allow direct entangling gates only between selected neighbors. When two qubits that are not directly connected need to interact, the quantum information may have to be moved through additional operations, or the circuit may need to be reorganized. These routing operations increase depth and create more error opportunities. A machine with fewer qubits but more favorable connectivity for a particular task can sometimes outperform a larger device whose topology requires heavy routing. This makes hardware comparison dependent on workload. There is no single ranking that captures every algorithm equally well. Error rate ties these properties together because every stage of the calculation contributes to whether the final result remains trustworthy. Gate errors, preparation errors, measurement errors, crosstalk leakage into unwanted states, and decoherence can all distort the computation in different ways. Some errors behave approximately independently. Others are correlated across qubits or across time. Some can be calibrated away partially. Others fluctuate. This complexity is why useful benchmarking cannot rely only on one simple average. A processor may perform certain gates extremely well while struggling with others. It may maintain excellent single-qubit control, but weaker entangling operations. It may perform well when qubits are used individually, and degrade when many are driven simultaneously. The practical capability of the machine emerges from the whole pattern, rather than from one headline figure. Despite these limitations, present processors have become scientifically valuable. They can prepare non-trivial entangled states, execute programmable circuits, explore many-body quantum dynamics, test compilation strategies, evaluate error mitigation methods, and serve as platforms for developing the control techniques needed for larger systems. They also allow researchers to study a question that could not be answered from theory alone: how quantum information behaves when an increasingly complex processor is operated as a complete system. The difficulty of scaling is not simply the difficulty of repeating a successful small experiment many times. New error mechanisms can appear as hardware grows, calibration becomes more complicated, control signals can interfere with one another, fabrication variation becomes harder to ignore. The classical electronics and software required to coordinate the device become larger engineering systems in their own right. Present machines are therefore useful, not only for the quantum circuits they run, but for exposing the practical obstacles that become visible only at scale. The most important shift in how these processors are judged comes from quantum error correction. A machine containing many physical qubits is valuable, but the deeper objective is to use those physical components to create logical qubits whose error rates are lower than the error rates of the underlying hardware. The distinction changes what progress looks like. If a larger error-correcting code produces a logical qubit that fails less often than a smaller code under appropriate operating conditions, the added physical complexity is doing useful protective work. This is qualitatively different from simply adding more unprotected qubits. The register is no longer growing only in size, it is beginning to grow in reliability. Experiments in quantum error correction have increasingly focused on this behavior, whether increasing the size or distance of a code can suppress logical errors rather than allowing the extra operations to introduce more failures than they remove. Demonstrating such suppression under controlled conditions is an important step because it addresses the central requirement for scalable fault tolerance. The goal is not merely to correct an isolated error once. The goal is to enter a regime in which additional redundancy makes the logical system progressively more dependable. Even then, a protected memory is only part of a full fault-tolerant computer. Logical qubits must perform gates without allowing physical errors to spread into logical failure. They must be initialized, measured, moved, and coupled while remaining protected. Some large algorithms require specially prepared resource states, whose production can consume substantial hardware and time. Classical decoders must interpret streams of syndrome measurements quickly enough to keep pace with the quantum system. The control stack must coordinate all of this while maintaining stable operation over long computations. Present experiments therefore represent steps along a hierarchy rather than one abrupt transition from noisy devices to complete fault tolerance. The field is gradually moving from demonstrating individual physical qubits to controlling larger processors to operating error-detecting codes to suppressing logical error, and eventually toward performing useful logical operations at scales that support demanding algorithms. This progression also clarifies why the phrase quantum advantage needs careful handling. A quantum processor can demonstrate a specialized experiment that is difficult to reproduce by straightforward classical simulation without yet solving a commercially valuable problem. The experiment may establish that the machine has entered a regime where its quantum behavior is genuinely challenging to emulate, but usefulness depends on more than difficulty. The task must matter, the result must be accurate enough, and the total cost of obtaining it must compare favorably with classical alternatives. Classical methods also continue to improve, often in response to quantum demonstrations, narrowing apparent gaps, or finding new ways to simulate structures once thought inaccessible. Quantum capability is therefore measured against a moving classical frontier rather than a fixed opponent. That competition is scientifically healthy because it forces both sides to become more precise. It replaces broad claims with specific questions about which task is being performed, at what scale, with what accuracy, and at what resource cost. The present state of quantum computing is best understood through this discipline. The machines already exist. They already perform controlled quantum operations beyond what early laboratory systems could manage. They are already useful for testing hardware algorithms, error models, and correction techniques. Yet the largest fault-tolerant applications remain beyond the reach of current unprotected processors. The important movement is not simply upward in qubit count, but inward toward better logical quality, lower error, deeper circuits, stronger connectivity, more stable calibration, and increasingly effective error correction. Once reliable logical qubits can be maintained and manipulated at sufficient scale, the discussion will change. The central question will no longer be whether quantum hardware can preserve a computation long enough to matter, but which problems deserve those protected logical resources in the first place. The most realistic uses of quantum computers begin with a narrower question than whether they will transform computing as a whole. The useful question is where the structure of a problem matches the strengths of quantum mechanics closely enough that the cost of building, controlling, and error-correcting the machine can be justified. This immediately separates plausible applications from broad claims of universal acceleration. Quantum processors are not naturally superior at ordinary office software routine databases, conventional graphics, or the majority of everyday numerical tasks. Their strongest prospects lie in specialized problems where amplitudes, phase entanglement, and quantum state evolution can represent something that classical computation handles only with great difficulty. Quantum simulation remains one of the clearest examples because the systems being studied are themselves quantum mechanical. Molecules, materials, magnetic systems, and many interacting particles are governed by rules that require the state of the whole system to be described through complex amplitudes and correlations. Classical computers can simulate many such systems with remarkable success, especially when approximation symmetries or specialized numerical techniques apply. The difficulty grows when the relevant quantum state becomes strongly correlated and resists simple compression. In those regimes, the amount of classical information required to represent the state can grow extremely quickly. A quantum computer does not need to store that same state as a giant classical list. It can represent quantum information directly within another controlled quantum system. This does not make every simulation efficient, and it does not remove the difficulty of extracting useful observables, but it changes the underlying representation. Chemistry is therefore a natural target. Many important chemical questions depend on electronic structure, energy levels, reaction pathways, and the interactions among electrons in molecules. Classical computational chemistry already provides powerful methods, but some systems remain difficult because accurate treatment of strong electronic correlation can become expensive. A fault-tolerant quantum computer could, in principle, implement algorithms that estimate molecular energies or simulate quantum dynamics with scaling advantages for selected problems. The practical value would depend on whether the improvement is large enough at chemically relevant precision and system size. A quantum algorithm that produces a theoretically elegant estimate, but requires an unrealistic number of logical operations would not yet be useful. The relevant comparison is always end-to-end the size of the molecule, the desired accuracy, the cost of state preparation, the number of logical qubits, the depth of the circuit, the overhead of error correction, and the performance of the best classical alternative. Material science follows a similar logic. Quantum properties determine superconductivity, magnetism, catalytic behavior, optical response, and many other effects that emerge from interacting particles. If quantum processors eventually simulate certain difficult material models more efficiently, they may help researchers investigate systems that are currently accessible only through severe approximations or enormous classical calculations. The value would not come from replacing all materials modeling. It would come from opening particular regimes where quantum correlations make classical methods especially costly. Cryptanalysis represents a very different application because the target is mathematical rather than physical. Shor's algorithm creates a clear theoretical threat to public key systems based on integer factoring and discrete logarithms if sufficiently large fault-tolerant quantum computers become available. This is one of the few quantum applications whose asymptotic significance is already well established. The uncertainty lies not in whether the algorithm changes the mathematical scaling, but in whether physical machines can reach the logical scale and reliability required to attack cryptographically important instances. The resource demands are substantial. Such a computation would require protected logical qubits, enormous numbers of reliable logical operations, and an error correction system capable of keeping the calculation stable throughout its full duration. This is why the security consequences of quantum computing are taken seriously, even though current machines cannot perform these attacks at meaningful cryptographic scale. The possibility is strong enough in theory that migration toward cryptographic methods designed to resist known quantum attacks can be justified long before a machine capable of breaking older systems exists. Optimization is more uncertain. Many real problems in logistics scheduling, finance, manufacturing, network design, and resource allocation can be expressed as searches through enormous spaces of possible solutions. This superficial resemblance to quantum superposition has encouraged interest in quantum optimization, but the connection is not automatically useful. Classical optimization is already supported by decades of sophisticated algorithms, heuristics, approximation methods, and specialized solvers. A quantum method has to compete against that moving target, including the cost of preparing the problem, running the circuit, sampling its output, and interpreting the result. Some quantum algorithms may provide advantages under particular assumptions or for particular mathematical structures, but broad commercial superiority across general optimization has not been established. The important distinction is between the existence of a quantum formulation and the existence of a practical quantum advantage. Many problems can be written as quantum circuits without becoming easier to solve. Linear algebra creates another field of interest because quantum algorithms can manipulate certain high-dimensional structures in ways that appear dramatically efficient under carefully defined conditions. Some theoretical algorithms promise large improvements for tasks involving systems of linear equations, matrix properties, or related transformations. Yet these claims often depend on assumptions about how data enters the quantum computer, how the matrix is accessed, what form the output takes, and which properties of the solution are actually required. If the goal is to reconstruct a full classical vector containing an enormous number of entries, the cost of reading that output may remove much of the apparent advantage. Quantum algorithms can be more promising when the desired answer is a global property that can be estimated without extracting every component individually. This repeats one of the central lessons of quantum computing: advantages often survive only when the question being asked fits the narrow output channel imposed by measurement. Quantum machine learning inherits many of these complications. Machine learning already relies heavily on large classical datasets, highly optimized numerical hardware and algorithms that continue to improve rapidly. Quantum methods have been proposed for classification, generative modeling, kernel estimation, optimization sampling, and linear algebra subroutines. Some theoretical results are interesting, and small experiments can test whether quantum circuits represent useful mathematical functions, yet large-scale practical advantage remains uncertain. Data loading can be costly. Noise can reduce the benefit of delicate quantum representations. Classical machine learning methods provide an extremely strong baseline. A quantum model that performs well on a small demonstration does not by itself establish that it will scale better, train faster, require fewer resources, or produce more useful predictions than classical systems. The appropriate stance is therefore neither dismissal nor assumption. Quantum machine learning is an active research area whose practical advantage must be demonstrated rather than presumed. This leads to a set of distinctions that are essential whenever applications are discussed. A theoretical quantum speedup means that under a specified computational model and set of assumptions, a quantum algorithm uses resources that scale more favorably than a classical comparison. This is a mathematical statement about complexity. Experimental quantum advantage is a different claim. It means that a real quantum device has performed some defined task in a regime that is difficult for available classical methods to reproduce within comparable conditions. Such an experiment can establish genuine computational separation without solving a problem of immediate economic value. Commercial usefulness adds another requirement. The task must matter outside the demonstration. The output must be accurate enough to support a decision or scientific objective, and the total quantum workflow must provide an advantage in time, cost, energy, capability, or quality that is meaningful compared with classical alternatives. These three standards can overlap, but they should never be treated as interchangeable. A quantum algorithm may have a theoretical speedup and no practical implementation. A processor may demonstrate experimental advantage on a specialized sampling task and no commercial application. A commercially useful system would require the quantum advantage to survive the entire chain, from problem preparation through error correction, computation, measurement, and interpretation. That final standard is the hardest because it includes everything that simplified demonstrations can temporarily ignore. It also explains why hybrid computation is likely to remain important. A useful quantum processor would not operate in isolation. Classical computers would still prepare data control, hardware, compile circuits, decode error syndromes, optimize parameters, analyze measurements, and perform the large amount of ordinary computation surrounding the quantum subroutine. The quantum component would be inserted where its particular structure creates enough value to justify using it. This makes the most plausible future less like a replacement of classical computing and more like an extension of it. Specialized accelerators already exist throughout computing with different hardware used for graphic signal processing, machine learning, and other workloads. Quantum processors may ultimately occupy a similarly specialized position, though for problems defined by quantum information rather than conventional parallel arithmetic. The applications that matter most may therefore be few in number and enormous in consequence. A machine does not have to improve every computation to become important. If it enables accurate simulation of a class of molecules that remained inaccessible, changes the security assumptions behind global cryptography, or solves a narrow mathematical task that constrains a major scientific or industrial problem, specialization would not diminish its significance. The unresolved issue is which of these possibilities will survive contact with full-scale engineering. Theory has identified places where quantum advantage can exist. Experiments have shown increasingly sophisticated control over quantum systems. What remains uncertain is where those two achievements will meet in a task whose usefulness is unmistakable. The future of quantum computing is not defined by one missing invention, but by a chain of engineering and scientific thresholds that must all be crossed together. A processor can gain more physical qubits without becoming more useful if those qubits are too noisy, too weakly connected, too difficult to control, or too expensive to protect. It can demonstrate increasingly sophisticated error correction without yet supporting the logical gate counts required by large algorithms. It can run a mathematically interesting quantum routine without showing that the same task matters outside the laboratory. This is why predictions about the field remain difficult. The theoretical model is mature enough to show that important quantum speedups are possible, but the route from that possibility to dependable large-scale machines passes through several layers of uncertainty. The first is physical scale. Useful fault-tolerant systems may require very large numbers of physical qubits, because each logical qubit must be protected by redundancy-repeated syndrome measurements, decoding, and fault-tolerant control. The exact overhead depends on the quality of the physical hardware, the error-correcting code, the architecture, and the computation being attempted. Better physical qubits reduce the burden. More efficient codes reduce the burden. Improved decoders, connectivity control, electronics fabrication, and calibration can reduce it further. Yet none of these improvements acts in isolation. A design that saves physical qubits but requires difficult long-range interactions may create a new engineering problem elsewhere. A design with excellent coherence may rely on slow gates. A platform with fast control may require demanding cryogenic infrastructure. The future is therefore not simply a race toward a larger qubit count. It is a race toward a complete system whose many constraints improve together. Quantum error correction sits near the center of this problem, because it determines whether scale can be converted into reliability. The critical question is not merely whether a code can detect errors in a small demonstration, but whether increasing protection continues to suppress logical failure as the system grows and operates for longer periods. If physical errors remain below the relevant threshold and the correction cycle can be executed reliably, a larger code can protect information more effectively. That principle creates the possibility of fault tolerance. But fault tolerance is not a single switch that changes a noisy processor into a perfect one. Logical operations still carry error. They simply carry far less error than the physical components beneath them, and the architecture is designed so that faults do not spread uncontrollably. Large algorithms may require logical failure probabilities to become extremely small, because a computation can contain vast numbers of protected operations. The longer the algorithm, the stronger the protection may need to be. This creates a direct connection between algorithm design and hardware cost. An algorithm that uses fewer logical qubits, but an enormous number of gates, may demand a different machine from one that uses more qubits but much less depth. The true resource is therefore not qubits alone, but reliable logical computation. The cost of producing one logical qubit is likely to remain one of the most important measures of progress. That cost includes physical qubits control, hardware, decoding capacity, cooling, or optical infrastructure calibration effort, and the operations required to keep the encoded state alive. A logical qubit that exists only briefly, or cannot participate in sufficiently accurate gates, has limited value. The aim is a logical system that can remain stable while meaningful algorithms are executed on top of it. Reaching that point at small scale would still leave the challenge of expansion. Thousands of logical qubits, or whatever a particular application ultimately requires, cannot be treated as independent laboratory demonstrations placed side by side. They form a coupled machine whose control, communication, error correction, and classical support systems must scale with the quantum hardware. The classical side of the architecture may become enormous. Syndrome data must be processed, control signals must be generated, circuits must be compiled into hardware-native instructions, calibration data must be tracked, measurements must be interpreted. Some algorithms require classical feedback during execution. A mature quantum computer may therefore look less like an isolated exotic processor and more like a deeply hybrid system, in which conventional computing surrounds a comparatively specialized quantum core. This hybrid structure also suggests how quantum technology may enter practical use. There is little reason to move ordinary computation onto qubits when classical hardware already performs it efficiently. The quantum processor is more likely to act as an accelerator for tasks that benefit from quantum structure, while classical machines handle the rest. A chemistry workflow, for example, could rely on classical methods for geometry preparation, data management, optimization, and interpretation, while assigning a difficult electronic structure subproblem to a fault-tolerant quantum routine. A cryptanalytic calculation could use a quantum algorithm for the portion that gains from period finding, and conventional arithmetic for the surrounding work. Even algorithms that are quantum at their mathematical core frequently require extensive classical preparation and post-processing. The boundary between the two forms of computation may therefore become increasingly practical rather than philosophical. Each machine does the work for which its architecture is best suited. The harder uncertainty concerns applications. Quantum simulation has a strong conceptual motivation, but not every quantum system is classically intractable, and not every inaccessible simulation has economic or scientific value. Cryptanalysis has clear theoretical significance, but it requires machines far beyond current unprotected processors for important targets. Optimization and machine learning contain many promising proposals, yet practical advantage remains conditional and must compete with powerful classical methods. Other applications may emerge that are not currently treated as the central justification for the field. History often shows that new computational capabilities acquire their most important uses only after hardware becomes stable enough for experimentation at scale. Quantum computing may follow that pattern, but it cannot be assumed in advance. The field has to demonstrate where advantage survives the full resource accounting. A theoretical speed-up is meaningful, but engineering decides whether it can be reached. Experimental advantage is meaningful, but usefulness decides whether anyone needs the result. Commercial value is meaningful, but only if the system can deliver it repeatedly accurately and at an acceptable cost. These layers of evidence should remain separate because combining them too early creates false certainty. The timeline is equally uncertain. Scaling a fault-tolerant architecture depends on advances in physics, fabrication control, engineering, cryogenics, or optic software algorithms and error correction. Progress in one area can accelerate another, but bottlenecks can also appear unexpectedly. A roadmap can describe intended milestones, yet it cannot guarantee when a difficult physical threshold will be crossed. The safest description of the future is therefore structural rather than chronological. The field must improve. Physical qubits prove that larger codes reduce logical error under realistic operation, perform increasingly complex fault-tolerant logical gates, reduce the resource cost of those operations, and then run algorithms whose advantage remains meaningful after all overhead is included. Each success narrows the uncertainty without removing it completely. If those steps continue, quantum computers may become extraordinarily important without ever becoming general replacements for classical machines. A specialized technology can still reshape science, security, and industry if the problems it solves are important enough. The comparison with ordinary computing can be misleading because the value of a machine does not depend on whether it performs every task. Scientific instruments are often transformative precisely because they do one narrow class of things that nothing else can do. A fault-tolerant quantum computer may eventually be understood in the same way, not as a universal fast computer, but as a new computational instrument for manipulating structures that classical machines represent only with difficulty. There remains, however, a wider possibility. If reliable logical qubits become plentiful, if algorithms improve, and if unexpected applications appear, the boundary of useful quantum computation could expand far beyond the areas now considered most plausible. That possibility is real enough to motivate research, but uncertain enough that it should not be treated as destiny. The future of quantum computing is therefore suspended between two outcomes that are not mutually exclusive. It may become a highly specialized technology used for a small number of exceptionally important calculations, and those calculations may still alter entire fields, or the combination of better hardware error correction algorithms and hybrid architectures may gradually broaden its role until quantum processing becomes a standard component of advanced computing infrastructure. What determines the result will not be the strangeness of quantum mechanics or the size of the promises made around it. It will be whether fragile physical qubits can be converted into reliable logical machines, whether those machines can run useful algorithms at realistic cost, and whether the problems they solve matter enough to justify everything required to keep quantum information alive. Quantum computing ends where it began, not with a machine that simply calculates faster, but with a different way of organizing information. Qubits carry amplitudes and phase rather than only definite classical values. Superposition opens a larger state space. Entanglement distributes information across relationships, and interference turns those relationships into patterns that measurement can reveal. Gates provide the control, algorithms provide the structure, and error correction offers a path toward keeping fragile quantum information intact, long enough for useful work. Beneath all of this sits a quieter fact. Quantum computing is difficult because nature does not freely expose the information stored in a quantum state. The same rules that make the computation unusual also limit how it can be observed, copied, protected, and scaled. That tension has shaped every major idea in the field, from the first qubit to the possibility of fault-tolerant logical machines. The future remains open. Some applications are grounded in strong theoretical results, while others remain exploratory. Some hardware approaches may scale further than expected, while others may encounter limits that redirect the field. Classical computers will continue to perform most computation, and quantum processors, if they mature, may become specialized partners, used only when their unusual structure offers something genuinely valuable. There is no need for the outcome to be universal for it to matter. A technology capable of solving even a narrow class of previously inaccessible problems could alter chemistry, materials, science, cryptography, or other areas in ways that are difficult to predict from the present. For now, quantum computing remains both a working technology and an unfinished experiment in how computation can be expressed through the laws of physics. Its deepest promise is not that every problem becomes easy, but that some problems may look fundamentally different once information itself is allowed to behave quantum mechanically.